Hello there and welcome to Science for Sleep, where curiosity settles in gently for the evening, and the universe slows down just enough for us to wander through it together. Tonight we're drifting far beyond the cities, satellites, and scattered signals of Earth, into places so cold, dark and quiet that for a very long time humanity didn't even realize they were there at all. Because hidden inside those enormous clouds drifting in the darkness, something extraordinary is constantly happening. New stars are being born, not all at once, of course. The universe rarely rushes anything important. A star does not simply appear one morning like a light bulb flickering on in a kitchen ceiling. It begins slowly, almost reluctantly, gathering itself over millions of years inside immense rivers of gas and dust. Entire solar systems begin in silence so complete that even the word silence feels too noisy for it. And somewhere out there tonight, while you lie here listening to this voice in your own quiet corner of the world, thousands upon thousands of newborn stars are opening their eyes for the very first time. Which feels slightly unfair, doesn't it? Some of them will live longer than mountains, oceans, continents, and perhaps even civilizations. Meanwhile, most of us feel accomplished if we remember where we left our phone charger before bed. Still, there's something strangely comforting about stellar nurseries. Maybe it's the idea that even in the coldest and emptiest regions of space, nature is still building things, slowly, patiently, constantly. The universe has not stopped creating, not even close. Before we begin tonight's journey though, I'd love to ask you something simple. Where are you listening from tonight? Is it late evening where you are? Early morning? Maybe rain is tapping softly against the window, or perhaps the room is completely still except for the sound of this video drifting through the dark. And if you find this voyage relaxing, interesting, or simply a nice place to let your thoughts slow down for a while, I'd be very grateful if you liked the video and subscribed. It helps this sleepy little corner of science continue finding people who need a calm place to land after long days. Now then, get comfortable, settle into your blankets, and let your breathing soften a little. Because tonight we're going somewhere very few human beings ever truly imagine properly. Not to a planet, not to a galaxy, but to the strange hidden regions where stars themselves begin. Oddly enough, the birthplaces of stars do not look dramatic at first glance. If you could somehow travel there in a spaceship and peer out the window, you might actually think something had gone wrong with the universe. No sparkling cities of light, no giant explosions every few seconds, no triumphant orchestral music swelling in the background as cosmic creation unfolds. Mostly, you would see darkness, great enormous stretches of it. The regions where stars are born are usually buried inside giant molecular clouds, vast drifting formations made mostly of hydrogen gas mixed with traces of helium, carbon, oxygen, and tiny grains of cosmic dust. These clouds are unbelievably large. Some span hundreds of light years across. That means light itself, moving at nearly 300,000 kilometers every second, would still take centuries to cross from one side to the other, and yet despite their gigantic size, they are astonishingly empty. This is one of the strange habits of the universe. Things can be enormous while also being incredibly thin. A stellar nursery might contain enough material to create thousands of stars, but the gas is spread so widely that if you stood inside one, you'd probably think there was almost nothing there at all. Earth's atmosphere feels thick by comparison. Even the best vacuum chambers humans have built in laboratories are often denser than parts of these clouds. Space, it turns out, is deeply committed to minimalism. Still, over immense spans of time, even sparse material can begin gathering together. Gravity is very patient. It doesn't need to rush. It simply keeps pulling, gently but endlessly, persuading atoms closer and closer together. And this is where the story truly begins. For millions of years, these clouds drift quietly through galaxies. Some are disturbed by nearby supernovas, massive stellar explosions that send shockwaves rippling. through space. Others collide with neighbouring clouds. Sometimes gravity alone is enough to begin the process. Tiny irregularities form. Slightly denser regions appear within the cloud, almost like wrinkles in fabric. Then gravity notices. That small pocket begins pulling in more gas. More material means more gravity. More gravity attracts even more material. Slowly, a runaway process begins. At first, nothing about this would look exciting to human eyes. There are no sudden flashes announcing that a star is under construction. In fact, the earlier stages are hidden completely inside thick cocoons of dust that block visible light. Astronomers only discovered many of these stellar nurseries by using infrared telescopes capable of seeing through the darkness. Ordinary visible light cannot easily escape these dense clouds. It gets scattered and absorbed by dust grains. But infrared light can slip through much more effectively, revealing warm objects hidden inside. Which means humanity spent most of its history completely unaware that entire generations of stars were quietly growing behind curtains of cosmic dust. That realization changed astronomy forever. Because once telescopes improved enough to peer inside these clouds, scientists discovered something astonishing. The galaxy was not calm and static. It was busy. Everywhere, stars were forming. Some regions resemble glowing caverns lit from within by young stars. Others look like towering pillars of gas stretching for light years. In places like the famous Eagle Nebula or the Orion Molecular Cloud Complex, gravity sculpts enormous structures that seem almost unreal. Great walls, arches, and columns drift through space like weather systems frozen in slow motion. Except these clouds are not made of water vapour. They are future suns, and perhaps future planets too. That part is especially strange to think about. Every atom inside your body was once part of ancient stars. The calcium in your bones, the oxygen you breathe, the iron in your blood, all forged long ago inside stellar furnaces. But before stars could create those heavier elements, stars themselves first had to be born from simple clouds of hydrogen left behind after the Big Bang. In a very real sense, star formation is one of the oldest ongoing stories in the universe, and it never truly stopped. Even now, somewhere inside the Milky Way, there are clouds slowly collapsing into newborn stars while you listen to this. Some of those stars may eventually host planets. Perhaps oceans. Perhaps living things staring upward at their own night skies, wondering where they came from. Not tonight, probably. They may need another few billion years first. The universe likes long timelines. This process also reveals something fascinating about how nature behaves on large scales. Humans often imagine creation as sudden. A switch flips, something appears, done. But cosmic creation is usually gradual. Stars spend millions of years simply becoming stars. Imagine waiting millions of years to begin your actual life. Human beings become impatient if a microwave takes longer than 90 seconds. Meanwhile, deep inside these clouds, gravity is conducting one of the slowest transformations imaginable. Gas falls inward, temperatures rise, pressure builds, material spins faster and faster as it collapses, flattening into disks around growing protostars. That spinning matters enormously. Without rotation, stars and planets might form very differently. But clouds in space are almost never perfectly motionless. Even tiny amounts of initial movement become amplified during collapse. It works a bit like figure skaters pulling their arms inward to spin faster. Except instead of a skater, imagine an object larger than solar systems. Eventually the centre grows hot enough for something extraordinary to happen, but not yet, not for a very long while. Before a star ignites, it passes through a strange, awkward phase astronomers call the protostar stage, which honestly sounds slightly adorable for an object destined to contain nuclear fusion powerful enough to outshine entire planetary systems. Protostars are messy things. They glow from heat generated by gravitational collapse, not from true fusion yet. Material crashes inward while powerful jets sometimes erupt outward from their poles at enormous speeds. Magnetic fields twist through surrounding gas. Radiation pushes against incoming material. Everything becomes turbulent and unstable. Young stars are not calm, gentle little candles quietly learning to shine. They are chaotic. Some fluctuate wildly in brightness. Others blast surrounding gas away with violent stellar winds. Entire nearby regions can be reshaped by these newborn objects before they even fully mature. Our own sun likely behaved this way too. That calm, warm star hanging in Earth's sky today was once a deeply unstable infant surrounded by a swirling disk of gas and dust. Long before oceans existed, before Earth formed, before dinosaurs or trees or people, the sun spent millions of years growing inside one of these dark stellar nurseries, and honestly, it probably would have looked terrifying. Immense flares, violent eruptions, radiation storms, constant turbulence. Not exactly the peaceful golden circle we draw in children's books. Though to be fair, children's books usually leave out most of the nuclear physics. What's especially remarkable is how difficult starbirth actually is. You might imagine gravity simply pulling everything together automatically, but nature keeps fighting the process at every stage. Gas pressure resists collapse, magnetic fields interfere, turbulence stirs clouds apart, radiation from nearby stars can disrupt entire regions before new stars finish forming. Many collapsing pockets never become stars at all. The universe produces a huge number of failures. Some objects gather enough mass to become brown dwarfs, strange in-between bodies too large to be planets, but too small to sustain proper hydrogen fusion. Astronomers sometimes call them failed stars, which feels slightly harsh considering they still become gigantic, glowing space objects. Imagine being labelled a failure despite being larger than Jupiter. Human standards can be unreasonable, yet this inefficiency matters. If every gas cloud instantly became stars, galaxies would burn through their material far too quickly. Instead, star formation unfolds gradually over billions of years, allowing galaxies like the Milky Way to continue producing new generations of stars even today. Right now, our galaxy creates roughly 1 to 3 new stars every year. That may sound modest for something containing hundreds of billions of stars already, but over cosmic timescales, it adds up continuously. And not all stars are alike. Some newborn stars become tiny red dwarfs that burn slowly for trillions of years. Others grow into massive blue giants so luminous they blaze through their fuel in only a few million years before exploding as supernovas. A star's fate is largely decided at birth. Its mass determines almost everything that follows. Lifespan, temperature, brightness, colour, final death. Which means inside these cold drifting clouds, the future of entire solar systems is already being quietly written. That includes planets too. Around many young stars, leftover material forms rotating disks. Within those disks, dust grains collide and stick together. Pebbles become rocks. Rocks become planetesimals. Eventually worlds begin assembling themselves piece by piece. Every planet starts as dust. That feels worth pausing on for a moment. Earth itself, every mountain, ocean, city, forest, animal and person once existed as microscopic particles drifting around a newborn sun inside a cloud of debris. The floor beneath your feet was once space dust. So was the coffee mug in your kitchen, and probably the spoon you forgot to wash earlier. Cosmic history has a funny way of making ordinary objects feel slightly more impressive. Astronomers studying stellar nurseries today are essentially watching the earlier stages of solar systems unfold. Modern telescopes like the James Webb Space Telescope can peer deeper into these dusty regions than ever before. Infrared instruments reveal disks forming around infant stars, jets blasting through surrounding clouds, and structures so intricate they almost resemble underwater coral reefs or smoke illuminated by distant firelight. except those glowing formations are often larger than the distance between stars. Scale in astronomy remains deeply unreasonable. One of the most famous nearby stellar nurseries is the Orion Nebula, located about 1,300 light-years from Earth. On clear nights, you can actually see it with the naked eye as a faint fuzzy patch beneath Orion's belt. That soft little blur in the sky contains thousands of young stars, some only a few 100,000 years old, which in stellar terms is practically infancy. If stars had human lifespans, these would still be in the hospital nursery wearing little socks. And Orion is only one small region inside a galaxy overflowing with stellar birthplaces. The Milky Way contains enormous molecular clouds spread throughout its spiral arms. Some remain quiet for ages, others erupt into bursts of star formation, where hundreds or thousands of stars emerge together in clusters. Stars are surprisingly social at birth. Most do not form alone. They emerge in groups, siblings born from the same collapsing cloud. Over time, these stellar families drift apart, scattering across the galaxy. Our own Sun likely formed alongside many sibling stars long ago, though those siblings are now lost somewhere among the Milky Way's hundreds of billions of stars. There may still be distant stars out there sharing the Sun's birthplace, ancient relatives wandering the galaxy unnoticed, and somewhere tonight, new stellar families are beginning their own journeys. That thought changes the night sky a little once you really sit with it. The stars overhead stop feeling static. They become part of an ongoing process. Birth, growth, aging, death, and renewal unfolding continuously across cosmic time. Some of the stars visible tonight are ancient survivors nearly as old as the galaxy itself. Others are comparatively young, and hidden inside dark clouds invisible to your eyes, future stars are already gathering themselves together for ages yet to come, which means the universe is not finished, not remotely. Even now, while Earth turns quietly through the dark and people drift off to sleep beneath countless different skies, gravity continues its slow, patient work inside enormous hidden nurseries far beyond human reach. Clouds collapse, gas spirals inward, temperatures rise, and somewhere deep within the darkness, another star is beginning to wake up. Long before a star begins shining, before nuclear fusion ignites deep inside its core, before planets circle around it or life eventually crawls across one of those worlds, wondering where it came from, there is only a cloud. Not a cloud in the earthly sense, of course. No soft white shapes floating through a blue afternoon sky. These are something far stranger, larger than entire solar systems, larger than distances the human brain comfortably handles. Vast drifting formations suspended inside galaxies, like slow-moving weather systems made from gas, dust, gravity, and time itself. And for most of human history, we barely understood what they were. If ancient people looked toward regions like the Milky Way stretching across the night sky, they saw glowing rivers of stars interrupted by dark gaps and shadows. Some cultures imagined celestial rivers, others saw smoke, pathways, animals, spirits, or openings into hidden worlds. But nobody truly knew that many of those dark regions were gigantic molecular clouds, enormous accumulations of material quietly waiting for gravity to begin building stars inside them. In fact, some of these clouds are so large that they contain enough raw material to create hundreds of thousands of stars, which means somewhere out there in the galaxy tonight are clouds holding future solar systems that do not exist yet. Future suns, future planets, perhaps future oceans, future storms, future forests, maybe even future civilizations sitting beneath unfamiliar skies, having their own sleepy conversations about astronomy. Though hopefully with slightly fewer online passwords to remember than we currently endure. The universe is already preparing places that may not fully emerge for millions or billions of years. That's one of the strange things about space. We tend to imagine it as empty, and technically it mostly is, but the emptiness is uneven. Some regions contain almost nothing at all for light years. Others collect material into enormous drifting concentrations. Over unimaginable spans of time, these concentrations become the starting points for nearly everything bright we see in the night sky. But before we go further, it helps to understand just how enormous these clouds truly are. Take the Orion Molecular Cloud Complex, one of the nearest major stellar nurseries to Earth. It stretches across hundreds of light years. Inside it are giant knots and filaments of gas dense enough to eventually collapse into stars. Astronomers estimate the total mass of the cloud is hundreds of thousands of times greater than our Sun. And yet if you somehow floated through it wearing a spacesuit, you might barely notice anything around you. That's because these clouds are incredibly diffuse. Their atoms are spread astonishingly far apart compared to anything we experience on Earth. Even the densest parts would qualify as a much better vacuum than nearly anything humans can create in laboratories. Space is deeply committed to spreading things out. Imagine taking all the air inside a room and stretching it across a region larger than continents. That still might be denser than parts of a molecular cloud. This creates a funny contradiction in astronomy. Some of the largest structures in galaxies are also some of the emptiest. Still, emptiness does not mean insignificance. Even sparse material matters when there is enough of it gathered over enough distance. Gravity does not care whether matter is concentrated tightly or scattered thinly. If mass exists, gravity responds, and gravity is endlessly patient. That patience is important because the early stages of star formation move extraordinarily slowly. Human beings are accustomed to fast transformations. We boil water in minutes, buildings rise in months, entire technologies become obsolete before our phone contracts end. The universe does not operate on those schedules. Inside giant molecular clouds, processes unfold over millions of years, sometimes tens of millions. Gas drifts quietly. Turbulence ripples through the cloud. Nearby supernovas send shockwaves passing through regions like distant thunder. Magnetic fields thread through everything invisibly. Nothing seems urgent. Yet gradually, tiny imbalances begin appearing. One region becomes slightly denser than the surrounding gas. Maybe a nearby stellar explosion compressed part of the cloud. Maybe galactic rotation stirred material together. Maybe turbulence created temporary knots that gravity slowly strengthened. At first, the difference is incredibly small, but gravity notices small differences, and once it does, the process becomes difficult to stop. These molecular clouds are made mostly of hydrogen, the simplest and most abundant element in the universe. Hydrogen has existed since shortly after the Big Bang itself. In many ways, stars are simply what happens when gravity gathers ancient hydrogen together tightly enough for nuclear fusion to ignite. That sounds simple. It absolutely is not simple. Nature places enormous obstacles in the way of star formation. Gas pressure pushes outward. Magnetic fields resist collapse. Radiation from nearby stars disrupts surrounding material. Turbulence constantly stirs the cloud internally. Many regions begin collapsing only to disperse again before a star can fully form. Galaxies are full of almost stars that never quite happen. Astronomers sometimes describe molecular clouds as turbulent environments, which is a wonderfully scientific way of saying everything inside them is messy. And they truly are messy. Rather than smooth uniform blobs, these clouds resemble tangled networks of filaments, knots, cavities, and arcs. Modern telescopes reveal structures that look uncannily like smoke drifting through water or storm fronts seen from above Earth's atmosphere. Except these structures may span dozens or even hundreds of light years. One especially fascinating aspect of these clouds is their temperature. Stellar nurseries are cold, extremely cold. Many regions hover only a few degrees above absolute zero, the coldest temperature physically possible. That means atoms move slowly enough for molecules to form. This matters enormously, because molecules behave differently from individual atoms. Molecular hydrogen helps clouds radiate heat away more effectively, allowing gravity to compress material further. Dust grains also play a major role, shielding inner regions from radiation and helping temperatures remain low enough for collapse to continue. In a strange way, coldness becomes the first requirement for creating stars hot enough to shine for billions of years. The universe often builds extreme heat from extreme cold, and those dust grains floating through these clouds are surprisingly important too. Cosmic dust sounds harmless, perhaps even slightly whimsical, but it is one of the great architects of the visible universe. These grains are made from heavier elements forged inside older stars that died long ago. Tiny particles of carbon, silicon, oxygen, iron, and other materials drift through space after supernovas scatter them across galaxies. Over time, that dust becomes incorporated into new molecular clouds, which means every stellar nursery is partly made from the remains of older stars. Astronomers sometimes summarize this beautifully by saying stars recycle the universe. Our sun itself formed from material enriched by previous generations of stars. So did Earth. So did you. Every atom heavier than hydrogen or helium inside your body once passed through ancient stellar furnaces before eventually becoming part of a drifting cloud again. Star formation is not simply creation, it is renewal. That process also explains why early stars in the universe were different from modern ones. Shortly after the Big Bang, almost no heavy elements existed yet. The first stars formed from mostly pure hydrogen and helium. Without heavier elements and dust to cool clouds effectively, those early stars may have grown enormous compared to many stars forming today. Some were likely hundreds of times more massive than our Sun. And massive stars live fast. They burn hotter, brighter, and far more violently than smaller stars. Many explode after only a few million years, scattering heavier elements back into space. Those elements then help future clouds form more complex stars, planets, and eventually chemistry capable of supporting life. So when astronomers study molecular clouds today, they are not just observing where stars come from. They are observing one stage in a giant cosmic cycle stretching back nearly to the beginning of the universe itself. Clouds create stars. Stars create elements. Exploding stars seed new clouds. New clouds create new stars. The process continues again and again across galaxies. Even the Milky Way itself is shaped partly by this ongoing cycle. Its spiral arms contain many of the galaxy's giant molecular clouds, because those regions compress gas more effectively. As clouds pass through spiral arms, conditions often become favourable for star formation. That's why spiral galaxies frequently appear filled with bright young blue stars tracing elegant curved patterns across their disks. Those glowing spiral arms are partly stellar nurseries in action, and within them, gravity keeps working quietly year after year, century after century, million after million. One particularly interesting thing about giant molecular clouds is how unstable they can become. Astronomers use something called the Jeans instability to describe the point where gravity overcomes internal pressure. If enough material gathers within a region and temperatures remain low enough, collapse becomes inevitable. Though inevitable in astronomy still tends to involve timescales longer than mammal evolution. Once collapse begins, clouds often fragment into smaller pieces. Instead of forming one giant star, a cloud may break apart into dozens, hundreds, or even thousands of dense cores. Each core can potentially become a separate star. This is why stars often form in clusters. The famous Pleiades cluster, visible from Earth as a tiny sparkling group of blue stars, formed together from the same parent cloud. So did many other stellar groups throughout the galaxy. Even our Sun likely had siblings once. Astronomers suspect the Sun formed within a crowded cluster of stars billions of years ago. Over time, gravitational interactions slowly scattered those sibling stars across the Milky Way until they became almost impossible to identify today. Somewhere out there are stars born beside our Sun, ancient relatives wandering the galaxy unnoticed. That thought changes the night sky slightly once it settles into your mind. Stars stop feeling isolated. Instead, they become part of enormous family trees stretching backward through countless generations of stellar birth and death. And molecular clouds are where those family trees begin. The interiors of these clouds can also become surprisingly violent, despite their quiet appearance from afar. Turbulence churns through them constantly. Supersonic shockwaves ripple across regions larger than solar systems. Nearby stars blast ultraviolet radiation into surrounding gas, carving enormous cavities into the cloud structure. Some stellar nurseries resemble battlefields between gravity trying to compress material and radiation trying to disperse it. The Orion Nebula offers a remarkable example. Young massive stars near its centre emit intense radiation, powerful enough to sculpt nearby gas into pillars and ridges. Ultraviolet light ionizes surrounding material, making parts of the nebula glow vividly. Yet inside denser, darker regions, new stars continue forming despite the chaos. Creation and destruction happen simultaneously. That pattern appears throughout the universe repeatedly. One generation of stars influences the next. Massive stars may trigger new star formation by compressing nearby gas with shock waves. Other times they prevent formation by dispersing clouds entirely. Stellar nurseries are not peaceful assembly lines quietly producing stars at predictable intervals. They are dynamic ecosystems, and some molecular clouds become truly enormous beyond normal human comprehension. There are giant molecular clouds containing millions of solar masses of material. Entire stellar populations may emerge from a single cloud complex over time. In starburst galaxies, where star formation becomes especially intense, enormous clouds collapse rapidly to create vast clusters of stars in relatively short cosmic periods. Those regions can glow so brightly they become visible across millions of light years. Yet all of it still begins with drifting cold gas. That's another recurring habit of the cosmos. The most spectacular structures often emerge from the simplest ingredients: hydrogen, dust, gravity, time, and patience beyond anything humans naturally understand. Interestingly, molecular clouds are difficult to observe directly in visible light because the dust inside them blocks so much radiation. Many appear as dark patches silhouetted against brighter backgrounds. Astronomers therefore rely heavily on radio telescopes and infrared observations to study them properly. Certain molecules emit characteristic wavelengths that reveal cloud structure and motion. Carbon monoxide, for example, becomes especially useful because molecular hydrogen itself is surprisingly hard to detect directly under many conditions. So astronomers often map invisible hydrogen clouds indirectly by tracking carbon monoxide emissions, which means humanity learned how stars are born partly by studying cosmic carbon monoxide drifting through invisible clouds larger than solar systems. Science can occasionally sound deeply suspicious out of context. Modern telescopes have transformed our understanding of these regions dramatically. Instruments like the James Webb Space Telescope now peer into stellar nurseries with extraordinary clarity. Infrared imaging reveals protostars hidden inside dusty cocoons, disks of material surrounding infant stars, and intricate cloud structures never previously visible. Some of the images almost look artificial because the scales and textures feel too strange for ordinary experience. Towering columns of gas, bright cavities carved by radiation, dense knots collapsing inward, streams of glowing material stretching across trillions of kilometers, and somewhere inside all of it, gravity keeps gathering matter toward future stars. One especially remarkable discovery is how filamentary these clouds often appear. Rather than random blobs, molecular clouds frequently organize into long thread-like structures. Stars tend to form where these filaments intersect or become especially dense. Why filaments emerge so commonly remains an active area of research, though turbulence, magnetic fields, and gravitational dynamics all likely contribute. The universe, it seems, enjoys building structures in patterns, even on gigantic scales. And yet, despite all this complexity, there is still something deeply quiet about stellar nurseries. Perhaps it's because everything happens so slowly compared to human life. No person could watch a molecular cloud collapse with their own eyes in real time. The process unfolds across spans longer than civilizations. Entire empires rise and vanish, while gravity patiently gathers gas together inside cold, drifting darkness. Meanwhile, Earth continues spinning beneath ordinary human concerns, emails, groceries, laundry, traffic. The strange thing is that both scales are equally real. Somewhere inside a giant molecular cloud tonight, atoms are beginning journeys that may eventually become stars billions of years from now. And here on Earth, someone is probably searching under couch cushions for missing headphones. The universe contains room for both experiences simultaneously. Still, those drifting clouds matter more to our existence than almost anything else in astronomy. Without them, no new stars would form. Without stars, no planets. Without planets, no chemistry complex enough for oceans, biology, or people quietly listening to science videos late at night wondering how stars are born in the first place. Everything begins here. Cold clouds drifting through galactic darkness. At first, almost nothing seems to happen. A giant molecular cloud drifts through the galaxy, carrying enough material to build thousands of stars, yet for immense stretches of time it remains cold, dark, and strangely uneventful. If you could somehow observe one over the course of a human lifetime, you probably would not notice any obvious change at all. No dramatic collapse, no visible movement, just a vast shadow suspended among the stars. But gravity is already there. It is always there. That is one of the defining characteristics of gravity compared to the other fundamental forces of nature. It never switches off. It does not become distracted. It does not tire. Even across enormous distances, it continues pulling matter toward matter with endless patience. And eventually, patience wins. The beginning of stellar collapse often starts with something incredibly small. A tiny density difference inside the cloud. One region becomes slightly thicker than the surrounding gas. Maybe a shock wave from a nearby supernova compressed it. Maybe turbulence stirred material together briefly. Maybe galactic motion squeezed the cloud during its passage through a spiral arm. The exact trigger varies, but once enough material gathers into one region, gravity quietly begins tipping the balance. That balance matters because molecular clouds exist in a constant tug-of-war between competing forces. Gravity tries to pull everything inward. Internal gas pressure pushes outward. Magnetic fields resist compression. Turbulence stirs the cloud chaotically like invisible storms. Radiation from nearby stars may heat sections unevenly. For millions of years, many clouds hover near equilibrium, not collapsing completely but not dispersing either. Then one region crosses a threshold. Astronomers call this the Jeans instability, named after British physicist Sir James Jeans. The concept is surprisingly elegant. If a cloud becomes massive enough, cold enough, and dense enough, gravity eventually overwhelms internal pressure. At that point, collapse becomes unavoidable, though unavoidable remains delightfully slow by human standards. Imagine balancing a pencil perfectly upright on its tip. Technically, it can remain stable for a moment, but eventually the tiniest disturbance causes it to fall. A collapsing nebula behaves somewhat similarly. Once the balance shifts too far toward gravity, inward motion begins, and once it begins, the cloud changes forever. The strange part is that gravity itself makes the collapse accelerate. As material falls inward, the central region becomes denser. Greater density means stronger gravity. Stronger gravity pulls material inward faster, increasing density even more. It becomes a runaway process, though runaway here still unfolds across spans longer than recorded human history. Inside the collapsing region, atoms and molecules begin moving closer together. Collisions become more frequent. Temperatures slowly rise. The cloud that once drifted quietly through near-empty space starts transforming into something more organised and energetic, and all of this happens invisibly at first. Visible light cannot easily escape the dense interior because dust absorbs and scatters it. To ordinary eyes, the region remains dark, but inside that darkness, gravity is reshaping entire future solar systems. One of the most fascinating things about collapsing nebulae is that they almost never collapse evenly. Nature dislikes perfect symmetry. Tiny irregularities become amplified during collapse. One side may contain slightly more material, another may rotate a little faster. Turbulence creates knots and filaments throughout the cloud. As gravity pulls inward, these imperfections grow increasingly important. The cloud begins fragmenting. Instead of one gigantic object forming, many smaller dense cores emerge throughout the nebula. Each core may eventually become its own star. That is why stellar nurseries often produce entire clusters rather than isolated suns. The universe tends to build stars in groups, and those groups can become crowded places. Inside some collapsing nebulae, stars form relatively close together by astronomical standards. Massive newborn stars blast radiation across nearby regions, while smaller protostars continue gathering material. Stellar winds carve cavities into the cloud. Shock waves ripple through surrounding gas. Jets erupt from infant stars at enormous speeds. Star formation is not a neat, orderly process politely taking turns. It is chaotic. Still, through all that turbulence, gravity continues its work steadily. Another important factor during collapse is angular momentum, which sounds complicated but can be understood with a simple comparison. Imagine an ice skater spinning slowly with arms extended. When the skater pulls their arms inward, they rotate faster. Collapsing nebulae behave similarly. Even if a cloud rotates only slightly at the beginning, inward collapse concentrates that rotation. As material falls toward the centre, the entire system spins faster and faster. This creates a major problem for gravity. If the cloud spun too quickly, centrifugal effects would prevent further collapse entirely. Instead of forming stars, material would simply spread outward again. Fortunately for future solar systems everywhere, nature has several ways of redistributing angular momentum. Magnetic fields help transport rotational energy outward. Turbulence redistributes motion throughout the cloud. And eventually, much of the collapsing material flattens into rotating disks around growing protostars. Those disks become extremely important later because they are where planets form, which means planetary systems begin appearing before stars are even fully born. The entire process is astonishingly interconnected. While gravity compresses the nebula inward, temperatures continue climbing inside dense regions. This happens because collapsing gas converts gravitational energy into heat. Atoms moving inward accelerate, collide more frequently, and transfer energy to one another. In the earlier stages, much of this heat escapes through radiation. The cloud can cool itself effectively enough to continue collapsing. But eventually, central regions become dense enough to trap more and more heat inside. Now the transformation starts accelerating. The core grows warmer, pressure rises, material falls inward faster, and somewhere inside the dense centre, a protostar begins emerging. But not yet a true star. That distinction matters. A protostar glows primarily because of gravitational collapse, not nuclear fusion. Gravity is still the dominant energy source. The core has not yet reached the temperatures necessary for hydrogen atoms to begin fusing into helium. That requires around 10 million degrees Celsius, which is slightly warmer than most home heating systems. Still, even before fusion begins, protostars can become surprisingly energetic. Material spiralling inward forms accretion disks around them. Friction inside those disks generates additional heat. Magnetic fields twist violently. Jets of plasma may erupt from the poles at hundreds of kilometers per second. Young stellar systems often look less like calm, celestial objects and more like cosmic construction sites. Messy, violent, unstable, and remarkably beautiful. Modern telescopes have revealed these early stages in extraordinary detail. The James Webb Space Telescope especially has transformed our ability to peer through dusty stellar nurseries. Infrared imaging exposes collapsing regions previously hidden from view, revealing glowing protostars buried deep inside nebulae. Some images show long dark filaments feeding material into dense stellar cores. Others reveal enormous disks surrounding young stars. In certain regions, jets blast outward in opposite directions like cosmic exhaust streams. Everything moves, everything evolves, even though the timescales remain vast. One especially interesting aspect of collapsing nebulae is that gravity alone does not determine a star's final mass. In principle, collapsing regions could continue gathering material indefinitely. But in reality, newborn stars eventually begin pushing back against their surroundings. Radiation pressure becomes important. Stellar winds emerge. Jets eject material outward. Nearby massive stars may disrupt surrounding gas entirely. At some point, accretion slows or stops. The final mass of the star becomes locked in, and mass determines almost everything about a star's future: its temperature, brightness, colour, lifetime, death. Massive stars burn hot and blue, living only millions of years before exploding as supernovas. Small red dwarfs burn slowly and efficiently, surviving for trillions of years. Medium stars like our Sun fall somewhere between those extremes. All those futures begin taking shape during collapse, which means inside giant molecular clouds, gravity is not simply creating stars, it is shaping the future architecture of galaxies. Interestingly, not every collapsing object succeeds in becoming a true star. Some gather substantial mass, but never enough to ignite sustained hydrogen fusion. These objects become brown dwarfs, strange intermediate bodies larger than planets, but smaller than stars. Brown dwarfs occupy one of astronomy's most awkward categories: too massive to behave like planets, not massive enough to behave like proper stars. Astronomers sometimes call them failed stars, though from another perspective they still seem fairly impressive. Some emit heat and faint light for billions of years. Others possess atmospheres with exotic cloud layers made of hot minerals or vaporized metals. Failure in astronomy remains relative. Even more curious, some collapsing cores may produce free-floating planetary mass objects entirely disconnected from stars. In a sense, certain planets may form directly from nebular collapse rather than inside planetary disks. The universe occasionally improvises, and that improvisation creates enormous variety across stellar systems. Some stars emerge alone, others form in binary pairs, some become part of crowded clusters, some possess massive planetary systems, others remain isolated. All of those outcomes begin during collapse. The surrounding environment matters enormously too. In crowded stellar nurseries, nearby massive stars can strongly influence neighbouring regions. Their ultraviolet radiation heats surrounding gas, slowing collapse in some places while triggering it elsewhere through compression. Supernova explosions may also trigger new waves of star formation. Imagine a massive star dying violently, blasting shockwaves through nearby clouds. Those shockwaves compress gas into denser knots. Gravity then takes over inside those knots, creating new stars from the remains of older ones. Starbirth and stellar death become linked together in cycles spanning entire galaxies. Our own Sun likely formed in such an environment. Evidence from meteorites suggests radioactive elements present during the early solar system were probably produced by a nearby supernova shortly before or during the Sun's formation. That means some ancient exploding star may have helped trigger the collapse of the nebula that eventually became our solar system. In a very real sense, Earth may owe part of its existence to a long-dead neighbouring star. Cosmic history tends to overlap like that, and all of it traces back to gravity quietly amplifying tiny differences inside drifting clouds. One thing humans often underestimate about gravity is how weak it actually is on small scales. A refrigerator magnet easily overcomes Earth's entire gravitational pull on a paperclip. You can lift your arm against the gravity of an entire planet without noticing. Yet gravity dominates the universe on large scales because it only attracts, it never repels. Electromagnetic forces often cancel out because positive and negative charges balance. But gravity keeps accumulating. More mass creates more gravity. More gravity gathers more mass. Given enough time, even an incredibly weak pull becomes unstoppable. Stars themselves exist because gravity never gives up. And collapse continues long after the first. Dense cores appear. Inside growing protostars, temperatures rise steadily toward fusion thresholds. Surrounding disks feed material inward. Jets carry excess angular momentum outward. Magnetic interactions twist and reconnect violently. Entire systems evolve continuously while buried inside thick clouds of dust and gas. To an outside observer using visible light, much of this activity remains hidden. But infrared telescopes reveal the truth. Stellar nurseries are busy places. Some regions produce stars rapidly. Others evolve slowly over tens of millions of years. In giant molecular cloud complexes, star formation may propagate through different regions over long periods, as shock waves and radiation reshape surrounding material. The clouds themselves are temporary structures on galactic timescales. Eventually, enough stars form that their radiation disperses the remaining gas. Stellar winds carve enormous cavities into the nebula. Supernovas may blast surviving material apart entirely. The nursery dissolves. What remains are stars, some clustered together, some drifting outward over millions of years, and perhaps around certain stars, newly forming planets beginning their own long journeys. That outcome feels almost impossible considering how quietly the process starts. A faint density fluctuation, cold hydrogen drifting through darkness, gravity pulling slightly harder in one tiny region, and from that, entire solar systems emerge. There is something deeply humbling about the slowness of it all too. Human beings often measure change in seconds, days, or years. Even civilizations think historically in centuries. Nebula collapse operates on completely different scales. By the time a typical star fully forms, entire species on Earth may have appeared and vanished if the process were happening here in real time. Mountains rise and erode faster than stars are born. Gravity works without urgency because it does not need urgency. The universe has time. There are places in the galaxy where light struggles to survive, not because the stars are absent, but because something enormous stands between the stars and everything beyond them. Thick curtains of dust and gas drift through certain regions of the Milky Way so densely that visible light cannot easily pass through. To human eyes, these places appear dark, almost empty, like holes carved into the glowing structure of the galaxy itself. For centuries, people looked at these strange dark patches with confusion. Some early astronomers thought they might literally be gaps where stars did not exist. Others imagined mysterious voids or hidden celestial smoke obscuring distant light. The truth turned out to be far more interesting. Those dark regions are often giant stellar nurseries, the concealed birthplaces of stars, and they are among the coldest, darkest, and most secretive environments in the universe. If you could somehow travel inside one, the experience would feel deeply strange. There would be no up or down, no solid ground, no familiar horizon. Surrounding you would be immense drifting clouds stretching across distances almost impossible to visualize properly. The darkness would not resemble nighttime on Earth. It would feel thicker somehow, not merely the absence of light but the presence of something blocking it. Even nearby stars might disappear behind dense veils of dust. Inside these regions, temperatures fall to only a few degrees above absolute zero. Molecules drift slowly through near-vacuum conditions. Tiny dust grains float silently for millions of years. Gravity works invisibly through everything while magnetic fields thread through the cloud like hidden scaffolding. And buried inside all that darkness, stars begin growing, The remarkable thing is that stellar nurseries are not rare oddities. The Milky Way contains many enormous molecular cloud complexes where star formation actively occurs. Some are relatively nearby in astronomical terms. The Orion Molecular Cloud Complex, for example, sits only about 1,300 light-years from Earth. Others stretch through the galaxy's spiral arms in gigantic cold formations invisible to ordinary sight. Astronomers often refer to these regions as molecular clouds because the temperatures are low enough for atoms to bond into molecules. Hydrogen exists mostly as molecular hydrogen, joined in pairs rather than floating separately, as individual atoms. That detail matters more than it may initially seem. Molecules allow clouds to cool more efficiently by radiating energy away into space. Cooler temperatures mean less internal pressure resisting gravity. Without that cooling, many clouds would never collapse enough to form stars at all. In a sense, stars are born in darkness because darkness helps clouds remain cold enough for gravity to win, and the darkness can become astonishingly complete. Some regions inside stellar nurseries are so dense with dust that visible light cannot penetrate them whatsoever. These areas are called dark nebulae, and they appear as giant black silhouettes against brighter backgrounds of stars or glowing gas. One of the most famous examples is the Horsehead Nebula in Orion. Seen through telescopes, it resembles a dark horse-shaped pillar rising against a glowing red backdrop. The shape exists because dense dust blocks light behind it. Similar dark structures appear throughout many stellar nurseries, forming towering columns, globules, and winding filaments. Some of them span multiple light-years, and yet they remain hidden to human eyes without special instruments. Modern astronomy changed dramatically once scientists learned how to observe the universe in wavelengths beyond visible light. Infrared astronomy especially transformed our understanding of stellar nurseries because infrared radiation can pass through dust much more effectively than visible light. Suddenly, regions that once appeared completely black became filled with hidden activity. Young stars glowed inside dense clouds. Protostellar disks appeared around infant suns. Jets erupted through surrounding gas. Entire clusters emerged where darkness had previously concealed everything. It was like discovering that apparently empty caves deep underground were secretly full of growing cities. The James Webb Space Telescope has revealed these environments in extraordinary detail. Infrared images now show intricate structures inside stellar nurseries that previous generations of astronomers could only imagine vaguely. Filaments twist through giant clouds like tangled roots. Cavities carved by young stars glow softly through the dust. Dense knots collapse inward while radiation streams through nearby gaps. Some images almost resemble weather systems viewed from high above Earth, except these storms may be larger than solar systems. One especially fascinating thing about stellar nurseries is how alive they seem despite their stillness. Human beings often associate darkness with emptiness or inactivity, but these regions are incredibly dynamic. Gas flows through narrow filaments. Shock waves ripple across clouds. Magnetic fields channel material inward. Radiation from nearby stars sculpts surrounding structures continuously. Everything changes, just very slowly. That slowness can make stellar nurseries feel oddly peaceful, despite the immense energies involved. A collapsing cloud may eventually create stars capable of unleashing enormous radiation and stellar winds, yet the process unfolds over millions of years. Compared to human timescales, even violent events inside nebulae appear calm. The universe often hides its most dramatic transformations behind patience. Inside many stellar nurseries, dense regions called Bok globules drift like isolated islands within larger clouds. These small dark clouds were named after astronomer Bart Bok, who proposed they might contain forming stars. At the time, not everyone agreed with him. Eventually, observations proved him correct. Many Bok globules do indeed harbour protostars buried inside thick cocoons of dust and gas. Some appear almost completely opaque in visible light, tiny pockets of darkness suspended against glowing nebula backgrounds, and somewhere inside them, gravity quietly builds new suns. That process remains deeply hidden during the earlier stages. As collapse progresses, the central protostar becomes hotter and denser, but surrounding dust traps much of the emitted radiation. Only infrared and radio wavelengths escape effectively. In some ways, stars spend part of their infancy concealed from the visible universe. There is something strangely fitting about that. Human babies arrive wrapped in blankets inside protected rooms. Young stars emerge buried inside clouds larger than planetary systems. Nature appears fond of nurseries. The environments inside these clouds can also become surprisingly crowded. In massive stellar nurseries, many stars form within relatively close proximity. Young stellar clusters may contain hundreds or thousands of stars packed into regions only a few light-years wide. This creates complicated interactions. Massive newborn stars emit intense ultraviolet radiation capable of ionizing surrounding gas. That ionized gas glows brightly, creating emission nebulae like the Orion Nebula. Stellar winds blast outward at tremendous speeds, carving bubbles and cavities into nearby material. Some young stars actively disrupt the very clouds that created them. The larger and hotter the star, the more dramatic the effect becomes. Massive O-type stars can shine millions of times brighter than the sun and emit enormous quantities of ultraviolet radiation. Their presence reshapes entire sections of stellar nurseries. The pillars of creation inside the Eagle Nebula provide a spectacular example. These towering columns of gas and dust are being eroded by radiation from nearby massive stars. Dense knots inside the pillars continue forming stars while the surrounding material slowly evaporates under intense ultraviolet light. It is both creation and destruction unfolding simultaneously. The universe rarely separates those processes cleanly. Interestingly, stellar nurseries often produce wildly different types of stars within the same cloud complex. Tiny red dwarfs may form alongside massive blue giants. Some stars gather huge planetary disks, others remain relatively isolated. Much depends on local conditions inside the cloud. Density, temperature, magnetic structure, turbulence, nearby radiation sources. Even small differences can alter outcomes dramatically. And yet all these stars share a common origin inside cold, dark nebulae. One reason stellar nurseries remained mysterious for so long is because interstellar dust is extraordinarily effective at blocking visible light despite its tiny total mass. Dust grains themselves are microscopic, often smaller than smoke particles, but spread across enormous distances they absorb and scatter starlight efficiently enough to obscure whole regions of the galaxy. Without dust, the Milky Way would look very different from Earth. Many hidden stellar nurseries would become directly visible. The dark lanes crossing the galactic plane would disappear. Distant stars would shine more clearly across vast regions currently concealed. But without dust, stars and planets might never form properly either. Dust helps cool clouds. Dust shields molecules from destructive radiation. Dust grains provide surfaces where certain chemical reactions occur. Dust later clumps together inside planetary disks to help build worlds. The same material that blocks our view also helps create the objects we're trying to observe. Astronomy occasionally feels like solving mysteries, while someone keeps hiding the clues inside the clues. The chemistry inside stellar nurseries becomes surprisingly complex too. Astronomers have detected water molecules, carbon monoxide, ammonia, methanol, formaldehyde, and many other compounds drifting through molecular clouds. Some regions contain organic molecules considered important precursors for life-related chemistry. This does not mean life exists inside nebulae, but it does mean the ingredients for complex chemistry become widespread long before planets form. In a sense, some of the chemical foundations for future biology begin assembling inside dark stellar nurseries themselves. That realization changed scientific thinking profoundly. For much of history, humans assumed the chemistry of life might be rare or unique. Modern astronomy increasingly suggests the universe manufactures organic compounds rather naturally under the right conditions, and stellar nurseries provide many of those conditions. Meanwhile, hidden deep inside the densest regions, protostars continue growing larger. At first they remain invisible except in infrared wavelengths. Then gradually they begin affecting their surroundings more dramatically. Accretion disks spin around them, jets erupt from their poles, radiation pressure pushes nearby material outward. Young stars are not quiet neighbours. Some of the jets launched by infant stars stretch for light years. These outflows slam into surrounding gas, producing glowing shock fronts called Herbig-Haro objects. Viewed through telescopes, they appear as luminous streaks and knots scattered across nebular regions. The first time astronomers realised young stars could launch such enormous jets, it came as a surprise. But stellar nurseries seem to specialise in surprises. Another fascinating aspect of these environments is how strongly magnetic fields influence them. Interstellar gas may appear tenuous, but electrically charged particles moving through the cloud generate magnetic structures threading across huge distances. These fields help shape collapsing regions. They channel material along filaments. They transport angular momentum away from protostars. They influence jet formation, and they may partly regulate how efficiently stars form within giant clouds. Astronomers can sometimes map magnetic field directions indirectly through polarized light emitted or absorbed by dust grains aligned within the cloud. So even in regions too dark for visible observation, the hidden structure of the nursery gradually reveals itself through careful study. The more scientists examine stellar nurseries, the more intricate they appear. And they are temporary places. That may be one of the strangest things about them. Giant molecular clouds can survive for millions or tens of millions of years, but eventually star formation transforms them completely. Radiation disperses gas, stellar winds carve cavities, supernovas blast remaining material apart. The nursery dissolves. What remains are stars. Some continue travelling together in clusters. Others drift apart slowly through the galaxy. Planets may eventually emerge around certain systems. In rare cases, perhaps life appears. But the dark cloud itself fades away. Its material becomes part of something new. Our own solar system likely formed inside such a nursery about 4.6 billion years ago. The original cloud that birthed the Sun no longer exists. It dispersed long before Earth even developed oceans. Every human being who has ever lived emerged from the remains of a vanished stellar nursery. That thought makes these dark clouds feel oddly familiar despite their distance. At some point during the collapse, the darkness begins to change. Not suddenly, not with a dramatic flash bursting across the nebula, like fireworks announcing a grand cosmic opening ceremony. The universe is usually far more subtle than that. But deep inside the dense collapsing core, something important begins happening for the very first time. The growing object at the centre starts becoming warm, then hotter, then brighter. And after millions of years hidden inside cold drifting darkness, the first faint light of a future star begins struggling outward through the surrounding cloud. This is the moment a protostar awakens, not yet a true star, at least not in the full sense astronomers mean. Nuclear fusion still has not fully ignited in its core. The temperatures are not yet high enough for hydrogen atoms to begin permanently merging into helium. That stage is still ahead. But the object is no longer merely a collapsing cloud either. Gravity has built something new, and what gravity creates during this stage is surprisingly violent. Human beings often imagine starbirth as peaceful. A warm glowing sphere quietly turning on somewhere inside a soft colourful nebula, while gentle orchestral music plays in the background. Modern astronomy has revealed something far messier. Young protostars are turbulent, unstable, chaotic objects surrounded by swirling disks, magnetic storms, erupting jets and enormous flows of collapsing material. The early life of a star resembles a construction site far more than a calm sunrise. At the centre of the collapsing nebula, gravity continues pulling huge quantities of gas inward, but the infalling material cannot simply plunge directly into the protostar itself. Remember, the original cloud possessed at least some rotation, even if only a tiny amount. As collapse proceeds, that rotation speeds up dramatically. The result is the formation of an accretion disk, a broad flattened structure of spinning gas and dust orbiting around the growing protostar. And these disks become astonishingly important. Everything surrounding future stars begins inside them. Planets, moons, asteroids, comets, potential future oceans, future atmospheres, perhaps future life itself. Long before the star fully ignites, the architecture of an entire solar system may already be taking shape inside the rotating disk around it. But during the protostar phase, the disk itself is still extremely active. Gas spirals inward continuously. Friction heats the material. Magnetic fields twist violently through the disk. Shock waves ripple across different regions. And all the while, the central protostar keeps growing larger and hotter. The heat during this stage comes mostly from gravitational collapse itself. As material falls inward, gravitational energy converts into thermal energy. Imagine compressing air rapidly inside a bicycle pump. The pump grows warm because squeezing gas together increases particle collisions and temperature. Now imagine doing that with an object containing more mass than planets. The temperatures rise enormously. Deep inside the protostar, pressure builds relentlessly. The central regions become increasingly dense as gravity crushes material inward. Over time, the core temperature may climb into the millions of degrees. Still not enough for full hydrogen fusion, but enough for the protostar to begin glowing strongly in infrared light. That infrared radiation becomes crucial because visible light still struggles to escape through the surrounding dust. The protostar remains deeply hidden from ordinary observation. Only infrared telescopes can peer effectively into these dense stellar cocoons. This is why modern astronomy changed so dramatically once infrared technology improved. Suddenly scientists could watch stellar infancy unfolding inside regions that previously appeared almost completely black. The James Webb Space Telescope has provided some of the clearest views ever captured of these environments. Hidden protostars glow deep inside dark clouds while surrounding disks and jets become visible in remarkable detail. Some systems appear almost alien in complexity, tangled structures of gas illuminated from within by growing stars. And one of the strangest things astronomers discovered is that protostars often begin launching enormous jets of material outward. At first glance, this seems backwards. Gravity is pulling matter inward toward the forming star, so why are jets blasting away from it? The answer involves magnetic fields and angular momentum. As material spirals inward through the accretion disk, magnetic interactions help redirect some of that energy outward along the protostar's rotational poles. The result is the formation of highly focused bipolar jets, narrow streams of ionized gas ejected at tremendous speeds. Some of these jets travel hundreds of kilometers every second, and they can extend for light years across surrounding space. Imagine newborn stars acting like gigantic cosmic pressure washers, blasting material through their surrounding nebulae. Nature rarely does things halfway. When these jets collide with nearby gas clouds, they create glowing shock fronts called Herbig-Haro objects. Through telescopes, these appear as bright knots and streaks scattered around young stellar systems. They're essentially impact zones where fast-moving stellar outflows slam into colder surrounding material. The first time astronomers realized infant stars produced these structures, it reshaped scientific understanding of star formation completely. Young stars were not passive objects quietly gathering mass. They actively reshape their environments, and they remain unstable for quite a long time. protostars often fluctuate dramatically in brightness. Some undergo sudden bursts of accretion, where enormous amounts of material fall inward over relatively short periods. These eruptions can temporarily increase luminosity many times over. One famous category called FU, Orionis, objects, experiences particularly extreme outbursts. During these events, accretion rates surge enormously, causing the young star to brighten dramatically for decades or even centuries. Astronomers are still working to fully understand why these bursts occur, but they reveal something important about stellar infancy. It is messy. The growing protostar is not yet balanced or stable. Material falls inward unevenly. Magnetic activity erupts unpredictably. Surrounding disks evolve continuously. Everything remains dynamic and turbulent, and through all this chaos, gravity keeps feeding the central object more mass. Inside the protostar itself, the pressure becomes almost unimaginable. The growing weight of overlying material compresses the core further and further. Temperatures continue climbing. Eventually, another interesting process begins. Before full hydrogen fusion ignites, many protostars briefly fuse deuterium, a heavier form of hydrogen containing one proton and one neutron. Deuterium fusion occurs at lower temperatures than ordinary hydrogen fusion and acts almost like a temporary pressure release valve. It slows the collapse somewhat, but only temporarily. The protostar still has much further to go before becoming a true main sequence star. The distinction between a protostar and a mature star matters because fusion fundamentally changes the balance of forces inside the object. During the protostar stage, gravity remains dominant. The object is still collapsing overall, though more slowly than before. Once hydrogen fusion ignites fully, outward radiation pressure from fusion reactions balances inward gravity. That balance creates long-term stellar stability. But protostars have not reached equilibrium yet. They are still becoming. One especially fascinating thing about this phase is how different protostars can become depending on their mass. Small protostars evolve relatively slowly. They gather material gradually and may spend tens of millions of years contracting toward the main sequence. Massive protostars evolve far more quickly and violently. Some begin nuclear fusion while still heavily embedded inside their natal clouds. The most massive stars may complete much of their formation process astonishingly rapidly by cosmic standards, perhaps in only a few 100,000 years, though even that remains comfortably longer than the lifespan of most household appliances. Massive protostars also create especially chaotic environments. Their intense radiation begins affecting surrounding gas very early. Stellar winds carve cavities into the cloud. Ultraviolet radiation ionizes nearby material, creating expanding bubbles of glowing plasma. Some massive young stars become so energetic that they effectively destroy the stellar nursery around them, which is a rather dramatic way to leave home. Meanwhile, smaller protostars like the early Sun evolve more gently. The young Sun almost certainly possessed powerful magnetic activity, intense flares, and strong stellar winds compared to today's relatively calm version. But it still followed a quieter evolutionary path than giant blue stars. That calmer evolution proved rather fortunate for Earth eventually. Massive stars often produce environments too violent for stable planetary systems to survive nearby for very long. Inside the accretion disk around a protostar, another remarkable process quietly begins unfolding. Dust grains drifting through the disk start colliding and sticking together. At first, the particles are microscopic. Tiny silicate grains, carbon compounds, ice crystals in colder outer regions. But over time, electrostatic forces help these grains cling together into larger aggregates. Pebble-sized objects emerge, then rocks, then larger planetesimals, all while the star itself is still forming. That timing surprises many people. Planet formation does not begin after stars fully mature. It overlaps with stellar birth itself. By the time a star reaches stable hydrogen fusion, Parts of its planetary system may already be well underway. The universe multitasks aggressively. And the disk structures surrounding protostars are extraordinary environments in their own right. Modern observations reveal rings, gaps, spirals, and asymmetries inside many young disks. Some of these structures may already indicate forming planets, carving paths through surrounding material. Astronomers are essentially watching the earlier stages of solar systems emerging in real time, though real time still involves processes unfolding over millions of years. One particularly beautiful example is the young star HL Tauri. Images captured by radio telescopes revealed an intricate disk structure surrounding the infant star, complete with multiple concentric gaps likely caused by forming planets. The image stunned astronomers because it showed planetary architecture appearing much earlier than some theories predicted. Nature had once again started building worlds sooner than expected. Protostars also emit powerful stellar winds during this stage. Charged particles stream outward continuously, interacting with surrounding magnetic fields and nebular material. Over time, these winds help clear away remaining gas and dust from the immediate vicinity of the forming star. Eventually, the protostar becomes increasingly visible as its surrounding cocoon thins, but before that happens, the object spends a long time hidden inside the nursery. There is something oddly fitting about that too. Stars begin their lives buried inside darkness, invisible to the outside galaxy, while they gather strength and mass. Only gradually do they emerge fully into view. The process feels almost biological in a strange cosmic way. A long protected development before entering the wider universe, and all the while, gravity remains the guiding force behind everything. Gravity feeds the disk. Gravity compresses the core. Gravity drives temperatures higher. Without gravity, none of it continues. But gravity alone cannot explain the complexity of what emerges. Magnetic fields, radiation, turbulence, angular momentum, chemistry, and shock waves all intertwine during this stage. Star formation turns out to be far more complicated than simply gas collapses inward. Astronomers spent decades gradually uncovering these details, and even now many aspects remain uncertain. How exactly do massive stars gather so much material despite their intense radiation pressure? What determines final stellar masses most strongly? How common are certain disk structures? How efficiently do planets form inside different environments? Stellar nurseries continue keeping many secrets. Still, one thing is clear. By the protostar stage, the future star has truly awakened. Not fully ignited yet, not stable yet, but no longer merely a collapsing cloud drifting unnoticed through darkness. Now it radiates heat. Now it shapes its surroundings. Now it begins interacting with the galaxy around it. One of the strangest things about star formation is how long it takes for anything truly dramatic to happen. Human beings tend to imagine creation as fast. A spark ignites, a machine starts, a light switches on. Even in nature, many transformations unfold quickly enough for us to watch directly. Storm clouds gather over hours. Volcanoes erupt in moments. Forests change across seasons. Stars operate on completely different schedules. A protostar may spend millions of years preparing to become a true star. During all that time, gravity continues compressing the object inward, while temperatures slowly climb toward the point where hydrogen fusion can finally begin. Millions of years. That span is difficult for the human brain to hold comfortably. Entire species appear and vanish over intervals like that. Oceans shift, ice ages come and go, mountains rise and erode. Meanwhile, somewhere inside a dark nebula, a baby star is still warming up. The reason for this enormous delay comes down to a balance between gravity and pressure. Gravity wants to crush the protostar inward continuously, but as the material compresses, it heats up. Hot gas creates pressure pushing outward against further collapse. The protostar becomes trapped in a long negotiation between these competing forces, And unlike a true star, it does not yet possess the stable internal engine needed to halt collapse permanently. That engine is nuclear fusion, specifically hydrogen fusion. To ignite sustained hydrogen fusion, the core temperature must rise to roughly 10 million degrees Celsius. Only at such enormous temperatures do hydrogen nuclei move fast enough to overcome their mutual electrical repulsion and fuse together. That repulsion is important. Hydrogen nuclei are positively charged, which means they naturally repel one another. Under ordinary conditions, they do not want to combine at all. The protostar's core therefore needs extraordinary pressure and temperature to force fusion reactions to occur. Gravity must effectively squeeze the core into becoming a star. And gravity works slowly. As the protostar contracts inward, gravitational energy converts into heat. This process is called Kelvin-Helmholtz contraction, named after physicists Lord Kelvin and Hermann von Helmholtz. They realized long before nuclear fusion was fully understood that gravitational collapse alone could power the Sun temporarily, though only temporarily. At the protostar stage, gravitational contraction is still the dominant energy source. The object glows because collapsing material releases energy as heat. But this process is inefficient compared to fusion. It can sustain the protostar only while contraction continues. Eventually something more stable must take over. Until then, the protostar remains in a long, awkward adolescence. And awkward really is an appropriate word for it. Young protostars are unstable, their brightness fluctuates, their disks churn violently, magnetic fields twist through surrounding material unpredictably. Jets erupt outward from the poles while gas continues spiraling inward through the accretion disk. Everything is still settling. Imagine trying to build a stable furnace while enormous storms continuously throw additional fuel into it from all directions. That is roughly the situation facing a protostar. The mass of the object determines a great deal about how this phase unfolds. Large protostars evolve much faster than small ones. Massive stars possess stronger gravity, which compresses their cores more efficiently. Temperatures rise rapidly. Fusion ignites sooner. Some extremely massive stars may begin hydrogen fusion while they are still heavily embedded inside their natal clouds, effectively becoming stars before the surrounding formation process fully ends. Smaller protostars evolve far more slowly. A low-mass red dwarf may take hundreds of millions of years to settle onto the main sequence fully. Medium stars like our Sun require roughly tens of millions of years. That means our Sun spent far longer forming than humans have existed as a species. And throughout that entire interval, the solar system itself was evolving simultaneously. Planet formation overlaps with stellar infancy in fascinating ways. Inside the rotating accretion disk surrounding the protostar, dust grains continue colliding and merging into larger structures. Pebbles become rocks. Rocks become planetesimals. Eventually, embryonic planets begin emerging, all while the central protostar is still slowly contracting. In a sense, planets begin assembling before the parent star even finishes growing up. The early solar system was likely a deeply chaotic place during this period. The young sun emitted powerful stellar winds and violent radiation burst far stronger than those produced today. Meanwhile, countless rocky bodies collided throughout the surrounding disk. Some impacts were catastrophic. One collision between the early Earth and a Mars-sized object likely created the Moon. Other impacts helped shape planetary atmospheres, rotational tilts, and orbital dynamics. So while the infant Sun spent millions of years preparing for ignition, the future planets around it were already undergoing violent transformation themselves. The entire system matured together. And throughout all of this, gravity remained relentlessly patient. That patience matters because collapsing protostars cannot simply freefall inward indefinitely. As density rises, internal pressure grows stronger. The core becomes increasingly resistant to further compression. The collapse slows. This creates a remarkable situation where the protostar radiates enormous amounts of energy, while still gradually shrinking over time. If you could somehow observe a protostar over millions of years, you would see it contracting slowly while becoming hotter and denser. The surrounding accretion disk would evolve continuously. Jets might fluctuate in strength. Nearby gas clouds would shift under the influence of radiation and stellar winds. Everything would appear dynamic, just at a pace completely detached from ordinary human experience. Astronomers therefore study many different protostars at varying stages of evolution to reconstruct the broader process. Since no human can watch one star form from beginning to end directly, scientists piece together the sequence like detectives reconstructing a long story from snapshots taken at different moments. And the snapshots reveal extraordinary variety. Some protostars gather mass efficiently from large surrounding disks. Others remain relatively small. Some develop highly organized jet structures extending for light years. Others appear more chaotic. Some are born in crowded stellar clusters flooded with ultraviolet radiation from nearby massive stars. Others form in relative isolation. The environment changes everything. In crowded stellar nurseries, neighbouring stars may strongly influence the growth of younger protostars nearby. Massive stars emit intense radiation capable of stripping gas from surrounding disks. Shockwaves compress some regions while dispersing others. Certain protostars may lose much of their surrounding material before they can gather additional mass. Others thrive in protected regions of the cloud. The universe does not distribute opportunity evenly. Another fascinating aspect of this long pre-ignition phase is the role of convection inside the protostar itself. As the interior heats unevenly, hot material rises while cooler material sinks. Giant convection currents circulate energy outward through the growing star. In some low-mass protostars, convection dominates nearly the entire interior structure. Imagine enormous rivers of plasma slowly circulating through an object larger than planets, and all of it hidden inside darkness. Magnetic activity during this phase also becomes extreme. Protostars rotate rapidly compared to mature stars. Combined with strong convection, this rapid rotation generates intense magnetic fields. These fields interact with surrounding disks and outflows continuously. Some protostars produce flares vastly more energetic than anything modern humans experience from the Sun today. The young Sun almost certainly did this too. Early Earth formed around a much more active and violent version of the Sun than the relatively stable star we know now. Solar storms, radiation bursts, and magnetic activity shaped the early solar system profoundly. Yet despite all that activity, the Sun still required millions of years before becoming a fully stable hydrogen-burning star. That delay sometimes surprises people, because stars feel permanent from a human perspective. The Sun rises every morning reliably enough that it appears timeless, but stars have life cycles, and infancy takes time, especially because fusion itself is difficult to ignite properly. One reason stars require such enormous mass is that gravity must compress the core strongly enough to achieve those critical temperatures. Objects below a certain threshold simply cannot sustain hydrogen fusion, regardless of how long they contract. These objects become brown dwarfs. Brown dwarfs occupy one of the strangest categories in astronomy. They form similarly to stars through gravitational collapse, but they never quite gather enough mass to ignite sustained hydrogen fusion. Instead, they spend long periods glowing faintly from residual heat and limited fusion of heavier hydrogen isotopes like deuterium. They're essentially almost stars. The mass threshold separating brown dwarfs from true stars lies around 8% of the Sun's mass, or roughly 75 times Jupiter's mass. Anything below that limit remains trapped permanently in stellar adolescence, which feels slightly tragic. Though to be fair, some brown dwarfs still possess temperatures hotter than molten lava, and atmospheres filled with exotic cloud systems made from vaporized minerals. Astronomical disappointment remains relative. Meanwhile, protostars above the threshold continue contracting toward ignition. As temperatures climb higher, the core conditions become increasingly extreme. Matter exists not as ordinary gas, but as plasma, a state where electrons separate from atomic nuclei. The protostar becomes a giant sphere of electrically charged particles compressed under immense pressure, and still gravity keeps pushing inward. One especially remarkable thing about the pre-ignition phase is how efficiently stars regulate themselves once fusion finally begins. Hydrogen fusion does not ignite all at once like a bomb. Instead, small regions begin fusing gradually. The energy released creates outward pressure opposing further collapse. If the core compresses too much, fusion rates increase, raising pressure and slowing contraction. If the core expands slightly, temperatures fall, fusion slows, and gravity compresses the star again. Stars become self-regulating systems. But before ignition fully stabilizes the star, there is a long transition period where the balance remains incomplete. Protostars therefore move through evolutionary tracks on diagrams astronomers use to compare stellar brightness and temperature. One important path is called the Hayashi track, where young stars contract while remaining relatively cool at the surface. Later, more massive protostars follow additional evolutionary stages before settling onto the main sequence. The details become wonderfully complicated. Astronomers adore wonderfully complicated things, and despite decades of research, many uncertainties remain about the precise mechanisms controlling stellar birth. Scientists continue studying how magnetic fields influence accretion, how disks evolve into planetary systems, and how young stars regulate angular momentum during collapse. Even something as familiar as the Sun still carries mysteries about its earliest years. Modern observatories continue revealing new details constantly. The James Webb Space Telescope has captured astonishing infrared views of young protostellar systems buried inside stellar nurseries. Dense clouds glow softly with hidden heat. Disks reveal intricate structures. Jets slice through surrounding gas. Some images show systems so young that the central protostar barely exists yet as a recognizable object. Others reveal stars approaching ignition while still wrapped inside remnants of their birth clouds. It is essentially astronomy's version of an infant photo album, except the babies are future suns, and the nursery spans light years. Perhaps the most humbling thing about this entire phase is how ordinary it is cosmically speaking. Every visible star in the night sky once passed through something like this. Every giant blue star, every quiet red dwarf, every sun with planets orbiting around it, all spent immense stretches of time hidden inside darkness, slowly gathering heat before fusion finally ignited. Our own sun did too. Long before Earth existed, before oceans or continents or life, the sun was simply another protostar buried inside a collapsing nebula, waiting patiently for ignition. And somewhere in the galaxy tonight, countless others are doing the same thing. Invisible young stars still warming themselves through gravity alone, their cores slowly growing hotter, their disks quietly assembling future planets, their jets carving pathways through surrounding clouds. After millions of years of collapse, compression, turbulence, and heat, the core finally reaches the threshold it has been moving toward since the very beginning. 10 million degrees. Perhaps more. Deep inside the protostar, conditions become so extreme that hydrogen nuclei begin doing something they normally resist with all their might. They start merging together, and in that moment, a star truly turns on. Not metaphorically, literally. This is the event that changes everything. Until now, gravity has dominated the entire story. Gravity gathered the nebula. Gravity compressed the cloud. Gravity heated the protostar. Every stage depended on matter falling inward under its own weight. But fusion changes the balance permanently. For the first time, the growing star begins generating enough internal energy to fight gravity properly from within. And what an extraordinary process it is. Hydrogen nuclei, which are simply single protons, naturally repel one another because they carry positive electric charge. Under ordinary conditions, they cannot get close enough to fuse. the electromagnetic force pushes them apart. To overcome that repulsion, temperatures must become unimaginably high. At around 10 million degrees Celsius, particles inside the core move so violently that some hydrogen nuclei collide with enough force to approach extremely close distances. Once they get close enough, another force takes over, the strong nuclear force. Unlike electromagnetism, which repels the protons, the strong force binds atomic nuclei together powerfully at very short ranges. If two hydrogen nuclei manage to get sufficiently close, the strong force essentially grabs them before electromagnetism can push them apart again. Fusion occurs, and when fusion happens, a tiny amount of mass disappears. Not much, just a very small fraction. But according to Einstein's famous equation, mass and energy are equivalent, E equals mc square, which means even a tiny amount of lost mass releases enormous energy. This is the engine powering stars. The Sun alone converts roughly 600 million tons of hydrogen into helium every second. Of that mass, around 4 million tons become pure energy radiating outward through space every second. And compared to larger stars, the Sun is actually fairly moderate. Massive blue stars burn through fuel at astonishing rates, producing energies almost difficult to describe meaningfully in everyday language. Yet all stars, regardless of size, begin with the same fundamental transformation. Hydrogen starts fusing. Gravity finally meets resistance. An equilibrium is born. That equilibrium is one of the most important balancing acts in the universe. Gravity continuously tries compressing the star inward. Fusion continuously produces outward pressure pushing against collapse. As long as those forces remain balanced, the star becomes stable. Astronomers call this stage hydrostatic equilibrium. The star has effectively reached adulthood. It no longer depends primarily on gravitational collapse for energy. Instead, fusion becomes the dominant power source. The long protostar phase ends. The object officially joins what astronomers call the main sequence, the long stable period where stars spend most of their lives. Our Sun has been in this phase for about 4.6 billion years already, and it will likely remain there for roughly another 5 billion more, which is comforting in a practical sense because without stable fusion, Earth would become a rather unpleasant place surprisingly quickly. Still, the moment fusion begins is not a single clean instant like flipping on a light switch. The transition unfolds gradually. Small fusion reactions start in localized regions of the core. Temperatures rise further, fusion rates increase, pressure builds outward more strongly. Eventually, the outward pressure becomes sufficient to halt the inward collapse. The star stabilizes, and from that point onward, everything changes inside the object. The interior structure reorganizes itself around fusion energy production. Radiation begins carrying enormous quantities of energy outward from the core. Convection currents may develop in outer layers depending on the star's mass. The star settles into its long-term identity. An identity matters enormously for stars because mass determines almost everything about what happens next. Small stars behave very differently from massive ones. A low-mass red dwarf ignites fusion slowly and gently. These stars burn hydrogen with extraordinary efficiency. Some may survive for trillions of years, far longer than the current age of the universe itself. In fact, the universe is not old enough for any red dwarf to have died naturally yet. Not one. Meanwhile, massive stars ignite fusion violently and burn through their fuel at tremendous speeds. A star 20 times more massive than the Sun may live only a few million years before exhausting its hydrogen supply. That difference surprises many people at first. Larger stars contain more fuel, so shouldn't they live longer? But gravity changes the equation. Massive stars possess much stronger gravity compressing their cores. Stronger compression creates much higher temperatures. Higher temperatures accelerate fusion enormously. The result is almost unfair. Big stars are born rich in fuel and spend it recklessly. Small stars live modestly and survive far longer. the universe occasionally resembles financial planning advice, and the newly ignited star immediately begins affecting its surroundings more powerfully than before. Radiation pressure intensifies, stellar winds strengthen, ultraviolet light floods nearby space. The remaining gas and dust surrounding the young star begin dispersing under this energetic assault. In many stellar nurseries, the birth of massive stars dramatically reshapes the environment around them. Radiation ionizes nearby hydrogen gas, causing nebulae to glow brightly. Expanding bubbles carve cavities into surrounding clouds. Shockwaves compress neighbouring regions. Sometimes these disturbances trigger new star formation elsewhere in the cloud. Other times they prevent it entirely by dispersing the remaining material. Young stars can be surprisingly disruptive neighbours. Our own sun likely cleared away much of the leftover gas from the early solar system through its solar wind during this stage. The young sun was far more magnetically active than today's relatively calm version. Flares erupted frequently. Radiation storms blasted through surrounding space. The early solar system was not peaceful. And yet, somewhere within that violent environment, Earth slowly assembled itself from dust and rock orbiting around the newly ignited sun. One especially fascinating thing about fusion ignition is how difficult it was for scientists to understand historically. For centuries, people did not know what powered stars at all. This became a serious problem in the 19th century because physicists began calculating how much energy the sun emitted. The numbers were enormous. Ordinary chemical burning could not possibly sustain such output for millions of years, let alone billions. Lord Kelvin and Hermann von Helmholtz proposed gravitational contraction as the energy source, and they were partly correct. Protostars really do shine through gravitational collapse initially. But their calculations suggested the sun could only shine that way for perhaps tens of millions of years. Geologists and biologists already suspected Earth was much older than that. Something was missing. The answer arrived gradually through advances in atomic physics during the early 20th century. Scientists eventually realized that fusion inside stellar cores could release far more energy than chemical reactions ever could. Then Einstein's equation explained why. Mass itself could become energy. Stars were not burning fuel like fires. They were transforming matter fundamentally. That realization changed astronomy forever. Suddenly, the universe became far older and more dynamic than previously imagined. Stellar evolution could now unfold across billions of years. Galaxies could contain multiple generations of stars enriching interstellar space with heavier elements. And perhaps most importantly for our existence, fusion inside stars could explain where many chemical elements actually came from. Hydrogen fusion primarily creates helium. Later, inside more evolved stars, additional fusion reactions produce carbon, oxygen, nitrogen, silicon, iron, and many other elements essential for planets and life. Every oxygen atom you breathe was forged inside a star. Every calcium atom in your bones. Every iron atom in your blood. Fusion inside ancient stellar cores manufactured the raw materials for biology long before Earth even existed. And that entire process begins here, at ignition. At the moment hydrogen first starts fusing inside the young star's core. There is something remarkable about the fact that stars spend so long preparing for this transition. Millions of years of collapse and heating finally culminate in the creation of a self-sustaining nuclear furnace capable of shining for billions more. Human beings build reactors with enormous engineering effort. The universe does it with gravity and patience. And even after ignition, young stars often remain turbulent for quite some time. T-Tauri stars, named after a famous example, are young low-mass stars that have recently ignited fusion but still exhibit strong magnetic activity and variability. They rotate rapidly, produce intense stellar winds, generate enormous flares, and remain surrounded by evolving protoplanetary disks. The newborn sun almost certainly passed through such a phase too. In fact, Evidence preserved inside ancient meteorites suggests the early solar system experienced strong bursts of radiation and energetic particles from the young sun. These events influenced chemical reactions inside forming planetary material. The infant sun was not yet the calm, dependable star modern humans know. It had a much wilder youth. Massive young stars become even more extreme. Their radiation pressure may become so powerful that it blows away surrounding gas entirely, exposing the star dramatically within the nebula. Entire regions of stellar nurseries light up under the influence of newly ignited massive stars. The Orion Nebula provides a beautiful nearby example. Much of its glowing structure is powered by radiation from young hot stars near its centre. Without them, the nebula would appear very different. The birth of stars literally illuminates their surroundings, and once fusion stabilizes the core, the star begins its long main sequence lifetime. This phase dominates stellar existence. Most stars spend the overwhelming majority of their lives quietly fusing hydrogen into helium in stable equilibrium. The Sun, for example, will remain on the main sequence for about 10 billion years total. Compared to the violent instability of stellar birth, the main sequence feels almost calm. But that calm rests atop extraordinary physics. Deep inside every star, fusion reactions continue relentlessly every second. Radiation generated in the core slowly diffuses outward through dense stellar material. In the Sun, a photon produced near the core may take hundreds of thousands of years to finally escape into space. Imagine light-spending geological timescales bouncing around inside a star before emerging into the universe. Stars are strange places, and all of it traces back to this turning point. The ignition of fusion, the end of gravitational adolescence, the birth of a true star. Somewhere tonight, hidden inside dark stellar nurseries across the Milky Way, countless protostars are approaching this threshold right now. Their cores continue heating. Pressure rises steadily. Fusion reactions flicker weakly at first, then stronger, then stable. Another star joins the galaxy. Another long-burning furnace turns on in the darkness, and somewhere around some of those newborn stars, disks of dust and gas continue quietly assembling future worlds beneath the light of suns that did not exist before. Once fusion begins and a star settles into stability, its future is already mostly decided. Not by luck, not by age, not by where it formed in the galaxy. Almost everything comes down to one thing: mass. The amount of material gathered during the star's birth determines nearly every major detail about its life, its brightness, its colour, its temperature, its lifespan, its eventual death. Whether it becomes a quiet red dwarf glowing for trillions of years, or a massive blue giant destined to explode violently after only a few million, a star's birth mass is essentially its destiny, and the differences can become extreme. Some stars barely qualify as stars at all. Others grow so enormous that they push the limits of what gravity itself can hold together. The universe produces an astonishing range of stellar sizes, from dim little red dwarfs smaller than half the sun's mass to monstrous giants, containing over 100 times more material than our sun. That may not sound immediately dramatic until you remember something important. Mass scales aggressively in stars. A star 10 times more massive than the sun is not merely 10 times brighter. It may shine tens of thousands of times more powerfully, and that extra brightness changes everything. To understand why, it helps to remember what a star actually is during the main sequence phase. Gravity tries to crush the star inward continuously. Fusion in the core generates outward pressure resisting collapse. The balance works beautifully, but the strength of gravity depends directly on mass. A more massive star experiences much stronger inward compression. The core becomes denser and hotter. Higher temperatures dramatically increase fusion rates, and fusion reactions are extremely sensitive to temperature. Slight increases in core temperature can accelerate fusion enormously. so massive stars burn through hydrogen at astonishing speeds compared to smaller stars. This creates one of the great ironies of stellar evolution. Large stars possess far more fuel, yet they die much faster. Imagine two campfires. One burns slowly and steadily through the night. The other erupts like someone poured industrial fuel on it and consumes everything within minutes. Massive stars behave like the second fire. They live intensely and briefly. Meanwhile, small stars sip their fuel cautiously over unimaginable spans of time. The smallest true stars in the universe are red dwarfs. These objects possess only a fraction of the Sun's mass, sometimes barely above the threshold required for sustained hydrogen fusion. They are cool, dim, small, and astonishingly long-lived. Some red dwarfs may survive for trillions of years, longer than the current age of the universe by enormous margins. Since the universe itself is only about 13.8 billion years old, no red dwarf has ever reached the end of its natural lifespan yet. Not one. Every red dwarf ever formed still exists somewhere. That fact feels almost absurd once you sit with it for a moment. Entire galaxies have collided and evolved while the oldest red dwarfs simply kept glowing quietly in the background. These stars survive so long partly because they burn fuel very slowly. But another important reason involves convection. In stars like the Sun, fusion occurs mainly in the core while outer regions remain relatively separate. Eventually the core runs low on hydrogen, even though hydrogen still exists in outer layers. But many small red dwarfs are fully convective. Material circulates throughout the entire star continuously. Fresh hydrogen gets mixed inward toward the core while helium gets distributed outward. The whole star participates in fusion efficiently. Red dwarfs waste almost nothing. They're essentially the universe's most economical stars. Not especially exciting, perhaps, but extremely practical. And because they are so efficient, red dwarfs dominate the galaxy numerically. Around 70 to 80% of all stars in the Milky Way are thought to be red dwarfs. The universe overwhelmingly prefers making small stars, partly because forming massive stars is difficult. Massive stars require enormous quantities of gas collapsing rapidly enough to overcome intense radiation pressure. Once a growing star becomes very luminous, its radiation begins pushing outward strongly against infalling material. At some point, the star starts blowing away the very gas trying to feed it. Massive stars almost disrupt their own births, yet somehow nature still manages to create them, and when it does, the results become spectacular. Large blue stars burn incredibly hot. Surface temperatures may exceed 30,000 degrees Celsius or more. They radiate huge quantities of ultraviolet light. Their stellar winds blast material outward at tremendous speeds. Some shine millions of times brighter than the Sun. If Earth orbited close to such a star, life as we know it would become rather difficult rather quickly. Not only because of the heat, the radiation alone would be catastrophic. Massive stars are deeply unreasonable objects. One famous example is R136A1, among the most massive stars ever discovered. Estimates suggest it may contain well over 100 times the Sun's mass, and shine millions of times more brightly. Stars like this push close to theoretical limits, where radiation pressure becomes almost too strong for the star to remain stable, and despite their immense size, they die astonishingly young. A star like R136A1 may survive only a few million years. Compare that to the Sun's expected 10 billion year main sequence lifetime, or a red dwarf's trillions. Massive stars essentially live like cosmic celebrities, bright, short-lived, and dramatically unstable. The Sun occupies a middle ground between these extremes. It is considered a medium-sized yellow dwarf, large enough to sustain stable fusion for billions of years, but not massive enough to burn uncontrollably fast. In many ways, stars like the Sun may provide especially favourable environments for planetary systems. They live long enough for planets to stabilise and potentially develop complex chemistry or life. Massive stars may die too quickly. tiny red dwarfs introduce other complications because many produce powerful flares and tidal locking effects for nearby planets. The Sun sits in a rather comfortable range. Astronomers sometimes call stars like the Sun ordinary, which feels slightly rude considering it powers all life on Earth. Still, compared to the galaxy's extremes, the Sun is fairly moderate. Not too big, not too small. Just enough mass for long-term stability, and that stability begins at birth. One especially fascinating thing about stellar mass is how sensitive star formation becomes to initial conditions. Slight differences during collapse can produce very different final stars. If a protostar gathers just a little more material, its future changes dramatically. Core temperatures rise higher, fusion accelerates, luminosity increases, lifespan shortens, death becomes more violent. The universe operates on thresholds constantly, and some collapsing objects never cross the stellar threshold at all. These become brown dwarfs. Brown dwarfs exist in the awkward region between planets and stars. They form like stars through gravitational collapse, but never gather enough mass for sustained hydrogen fusion. They glow faintly from residual heat and limited deuterium fusion for long periods before gradually cooling. Astronomers sometimes describe them as failed stars, though that wording seems somewhat unfair considering some brown dwarfs possess storms larger than planets and atmospheres hot enough to vaporize metals. Failure remains relative in astronomy. Still, brown dwarfs reveal something important about star formation. Not every collapsing core succeeds equally. Some become giants, some barely survive, and environment matters too. Stars forming in dense stellar nurseries may compete for material. Nearby, massive stars can disrupt surrounding gas with radiation and winds. Some protostars continue accreting mass successfully, while others lose access to additional fuel. In crowded regions, stellar birth resembles cosmic urban development. Limited resources, chaotic interactions, occasional violent disturbances, and certain stars ending up far wealthier than others. Massive stars also tend to form in clusters alongside many smaller stars. The Orion Nebula offers a nearby example. Hot young stars near its centre illuminate surrounding gas while countless smaller stars continue forming nearby. The larger stars dominate the environment energetically despite being far rarer numerically. One massive star can influence entire sections of a nebula through radiation alone. Meanwhile, thousands of tiny red dwarfs glow quietly, almost unnoticed. The galaxy itself reflects this imbalance beautifully. Most stars are small and dim, but the stars humans notice most easily tend to be large and bright, because they dominate visible light. The night sky slightly misrepresents the universe that way. It highlights the loudest objects rather than the most common. Another remarkable consequence of stellar mass involves internal structure. Small stars often remain fully convective. Medium stars like the Sun possess radiative cores and convective outer layers. Massive stars may reverse that structure, developing convective cores and radiative envelopes. Different masses create different stellar architectures entirely. Fusion pathways change too. The Sun primarily uses the proton-proton chain to fuse hydrogen into helium. Massive stars rely more heavily on the CNO cycle, a more temperature-sensitive fusion process involving carbon, nitrogen, and oxygen as catalysts. Bigger stars do not simply burn more fuel, they burn it differently, and eventually all those differences shape how stars die. Small red dwarfs may simply fade gradually over unimaginable timescales. Sun-like stars expand into red giants before shedding outer layers and leaving behind white dwarfs. Massive stars undergo catastrophic core collapse and explode as supernovas, creating neutron stars or black holes. The violence of stellar death scales with mass too, which means a star's entire future story exists latent inside its birth conditions from the beginning. There is something oddly human about that idea. Tiny differences early in development leading to radically different lives later on. Except in this case, the tiny differences involve enough mass to create objects millions of kilometers across. Astronomy always escalates the scale aggressively. Modern telescopes continue helping astronomers understand how these mass differences emerge during star formation. Observatories like the James Webb Space Telescope peer into stellar nurseries revealing young stars at various stages of growth. Some protostars already dominate their surroundings despite their youth. Others remain faint and low mass. Disks evolve differently around different stellar types. Radiation reshapes nearby gas continuously. The complexity is enormous, and scientists still do not fully understand why nature produces the exact distribution of stellar masses observed throughout galaxies. Why does the universe prefer making small stars? What determines how much mass a protostar ultimately gathers? How do turbulence, magnetic fields, and radiation interact during collapse? These remain active research questions. Stellar birth still hides many secrets. But one thing is clear, mass determines destiny. A star born slightly too small never truly ignites. A star born moderately sized may shine calmly for billions of years. A star born enormous becomes a blazing giant living fast enough to alter entire regions of the galaxy before dying violently. And somewhere, hidden inside dark molecular clouds across the Milky Way, new protostars are still gathering mass right now. Some will remain small, quiet red dwarfs glowing long after galaxies evolve beyond recognition. Others will become gigantic blue stars burning so fiercely that their lives end almost as soon as they begin. Gravity is still deciding their futures. Once a young star finally ignites fusion, the surrounding stellar nursery does not suddenly become calm. Quite the opposite. In many ways, the chaos intensifies. The moment a star truly turns on, it begins fighting against the very cloud that created it. Radiation pours outward. Stellar winds accelerate into surrounding space. Magnetic storms erupt across the surface. Jets continue blasting material through the nebula. Young stars are not gentle newborns. They are loud, violent, energetic, and capable of reshaping enormous regions of space around them. This part of stellar birth surprised astronomers greatly when they first began observing young stars closely. Earlier generations often imagined stars forming quietly inside nebulae, and then gradually settling into stable existence. Modern astronomy revealed something far more turbulent. Stellar nurseries can resemble battlefields. Gravity still tries pulling gas inward toward forming stars, while radiation and stellar winds push material outward. Shockwaves collide. Magnetic fields twist through collapsing disks. Massive stars carve cavities into surrounding clouds with intense ultraviolet light. Entire sections of nebulae may be ripped apart by the very stars they produced. The universe has a habit of turning creation into controlled destruction. One of the first major forces shaping these environments is stellar wind. A stellar wind is a continuous outflow of charged particles streaming away from a star. The modern sun produces such a wind even today. Every second, billions upon billions of particles flow outward through the solar system. Earth's magnetic field protects us from much of this stream, though interactions still produce beautiful auroras near the poles. But the young sun was far more violent, and many newborn stars are even worse. Young stars rotate rapidly and possess extremely strong magnetic fields. Their surfaces erupt with flares, plasma loops, and energetic outbursts. The resulting stellar winds become much more intense than those produced by mature stars. Imagine the solar wind today, then increase its strength dramatically. That was the environment surrounding many infant planetary systems, and these winds matter enormously because they help clear away leftover gas and dust from around the young star. In the earlier stages, the protostar remains deeply buried inside dense material, but over time, stellar winds and radiation begin excavating cavities through the surrounding nebula. The star slowly emerges from its cocoon, though slowly, still involves millions of years. One especially fascinating thing about stellar winds is how strongly magnetic fields shape them. Young stars behave somewhat like gigantic electromagnetic engines. Plasma flowing through their magnetic fields becomes accelerated outward into space. Twisted magnetic loops reconnect violently, releasing huge bursts of energy. Some flares produced by young stars dwarf anything humans have observed from the Sun in recorded history. And these eruptions can have dramatic consequences for nearby planets forming inside surrounding disks. Modern astronomers studying exoplanets increasingly realize that stellar youth may strongly influence planetary evolution. A young star's radiation and stellar wind can strip atmospheres away from nearby worlds. Powerful ultraviolet light alters chemistry inside planetary disks. Charged particles bombard forming planets continuously. The early years of a solar system are dangerous. Earth itself likely survived an extremely hostile environment during the Sun's infancy. The young Sun rotated faster, generated stronger magnetic storms, and emitted far more energetic radiation than today's stable, middle-aged version. If modern humans had somehow visited the early solar system, they probably would not have enjoyed the weather. Meanwhile, larger stars become even more extreme. Massive newborn stars produce tremendous amounts of ultraviolet radiation, capable of ionizing surrounding hydrogen gas. When hydrogen atoms absorb enough energy, their electrons separate from their nuclei, creating glowing plasma regions called H2 regions. This is why many stellar nurseries shine so brilliantly in astronomical images. The glow often comes from ionized gas illuminated by hot young stars embedded within the cloud. The famous Orion Nebula is one beautiful example. Young massive stars near its center flood the surrounding nebula with ultraviolet radiation, causing enormous regions of gas to glow visibly. Without those stars, much of the nebula would remain dark. Young stars literally illuminate their birthplaces. But illumination comes with consequences. Radiation pressure from massive stars can become so intense that it physically pushes gas outward. Combined with stellar winds, this creates expanding bubbles and cavities inside molecular clouds. Some cavities stretch for dozens of light years. Imagine a newborn star effectively blowing enormous holes through the nebula around it. Massive stars are deeply inconsiderate neighbours. The famous pillars of creation inside the Eagle Nebula reveal this process dramatically. These towering columns of gas and dust are slowly being eroded by ultraviolet radiation from nearby young stars. Dense knots inside the pillars continue forming stars while the surrounding material evaporates under the assault. The structures look peaceful in images. In reality, they are under attack continuously, and eventually the pillars themselves will disappear entirely. This interplay between creation and destruction appears throughout stellar nurseries constantly. Radiation from massive stars may trigger new collapse in some nearby regions by compressing gas clouds. Elsewhere, the same radiation may prevent star formation by dispersing material too quickly. Young stars shape the destiny of neighbouring stars. The nursery becomes an ecosystem of competing forces, and inside all this chaos, planetary systems continue trying to form. That may be the strangest part. While stellar winds blast outward, and radiation storms sweep through surrounding space, dust grains inside protoplanetary disks still collide and stick together gradually. Planetary embryos continue growing amid the turbulence. The process feels almost improbable, yet it works repeatedly across the galaxy. Modern telescopes have captured extraordinary images of protoplanetary disks inside violent stellar nurseries. Some disks appear sharply eroded on the side facing nearby massive stars. Others develop long tails of gas stripped away by radiation. Astronomers call some of these structures proplids, short for protoplanetary disks. The Orion Nebula contains many famous examples. Young stars there possess disks illuminated and sculpted by nearby ultraviolet radiation. Some may eventually form planetary systems despite the hostile environment. Others may lose much of their material before planets fully emerge. The universe does not guarantee successful outcomes. One especially dramatic phenomenon inside stellar nurseries involves shock waves. Shock waves form whenever fast-moving material slams into slower gas. Jets from young stars create them. Stellar winds generate them. Supernova explosions send enormous shock fronts rippling through molecular clouds, and these shock waves can become incredibly energetic. Herbig-Haro objects provide beautiful examples. These glowing regions appear where jets from infant stars collide with surrounding gas at high speeds. The collisions heat material enough to produce visible emission. Viewed through telescopes, they resemble luminous streaks or knots suspended within dark nebulae. Essentially, they are cosmic impact zones. The young stars producing them may still remain hidden deep inside surrounding dust. There is something wonderfully dramatic about that. Invisible infant stars firing plasma jets across light years while buried inside dark clouds. Stellar nurseries refuse to behave quietly. And then there are the magnetic fields. Magnetism plays an enormous role during stellar infancy. Young stars possess extremely strong magnetic activity because of their rapid rotation and turbulent interiors. Magnetic fields connect the star to its surrounding disk in complex ways. Sometimes these magnetic interactions become unstable. Field lines twist, stretch, reconnect violently. Huge bursts of energy erupt outward. Astronomers observe some young stars producing flares thousands of times more powerful than typical solar flares today. These flares flood nearby space with X-rays and energetic particles. Again, not ideal conditions for a peaceful planetary childhood. Still, the early Earth somehow survived all this. In fact, some scientists suspect the young sun's activity may have influenced Earth's early chemistry significantly. Energetic radiation and charged particles could have helped drive certain atmospheric reactions important for prebiotic chemistry. Violence and habitability may not be entirely incompatible. The same cosmic chaos that threatens planets may also shape them in important ways, and sometimes the chaos becomes catastrophic. Massive stars live short, violent lives. Some explode as supernovas only a few million years after forming. These explosions release enormous amounts of energy, briefly outshining entire galaxies. If a supernova occurs near an active stellar nursery, the consequences become dramatic. Shock waves race through surrounding clouds. Radiation floods nearby regions. Gas compresses violently. New waves of star formation may begin, or existing protostars may be disrupted entirely. Stellar nurseries are not isolated from galactic events. They exist inside constantly evolving environments shaped by neighbouring stars, magnetic fields, galactic rotation, and occasional explosions. Everything interacts. That complexity is one reason astronomers still struggle to model star formation perfectly, even with modern supercomputers. The physics involved spans enormous ranges of scale and behaviour simultaneously. Gravity, hydrodynamics, radiation transport, magnetic fields, plasma physics, chemistry, shock waves, turbulence, all interacting continuously across distances larger than solar systems. The universe does not simplify problems for researchers, yet despite all this violence, stars continue forming successfully throughout galaxies everywhere. The Milky Way creates roughly 1 to 3 new stars each year even now. Other galaxies undergoing intense starburst periods may produce hundreds, and many of those stars emerge inside deeply chaotic environments. Perhaps chaos itself is partly necessary. Turbulence inside molecular clouds may help create the dense filaments and cores where collapse begins. Shock waves may compress gas into star-forming regions. Magnetic fields regulate angular momentum and outflows. What appears destructive from one perspective may actually help sustain the broader cycle. The universe often builds through disruption. One particularly fascinating example of stellar violence involves Wolf-Rayet stars, massive stars shedding enormous quantities of material through powerful winds. These stars lose mass so aggressively that their outer layers strip away over time, the winds can reach millions of kilometers per hour. Entire nebulae may form from material blasted outward by such stars, and many Wolf-Rayet stars likely formed in crowded stellar nurseries where their radiation and winds strongly influenced neighbouring star formation. Massive stars live like cosmic hurricanes, brief, intense, and transformative. Meanwhile, smaller young stars continue their slower evolution amid the surrounding turbulence. T-Tauri stars, the young equivalents of sun-like stars, remain magnetically active for millions of years after fusion begins. Their disks evolve continuously, while planets slowly assemble within them. Some disks produce giant planets quickly, others form rocky worlds gradually. Some may fail entirely. Again, outcomes vary enormously. And through all of it, the surrounding nebula keeps changing. Cavities expand, pillars erode, jets carve pathways through gas, radiation sculpts cloud edges into strange shapes. Eventually enough stars form that the original molecular cloud begins dispersing completely. The nursery slowly tears itself apart. What remains afterward are stars, some still surrounded by planetary disks, some already hosting newly formed planets, some destined to die violently in the relatively near future, others likely to glow quietly for trillions of years, all born from the same chaotic environment. And somewhere tonight inside the Milky Way, this process continues unfolding right now. Young stars blasting radiation through surrounding clouds, jets streaking across hidden nebulae, shockwaves rippling through cold gas, magnetic storms erupting around infant suns, planetary systems struggling into existence amid turbulence and stellar violence. The galaxy remains full of noisy newborn stars still fighting their way out of the darkness that created them. Not long after fusion begins, young stars enter one of the strangest phases of their lives. They are finally true stars now. Hydrogen fusion burns inside their cores. Gravity and pressure have reached a temporary balance. The long collapse phase is mostly over. And yet these stars are still deeply unstable. Astronomers call many of them T-Tauri stars, named after a young variable star in the constellation Taurus that became the prototype for this stage. These objects are essentially stellar teenagers, moody, energetic, unpredictable, and occasionally destructive. The comparison is honestly more accurate than it sounds. T-Tauri stars are young sun-like stars still adjusting to their new existence. They have recently ignited fusion, but remain surrounded by evolving disks of gas and dust. Their magnetic fields are extraordinarily active. Their brightness fluctuates. Their surfaces erupt with violent storms and flares. They are not calm, stable stars yet. They are still growing into themselves. This stage is especially important because our own sun almost certainly passed through it billions of years ago. Long before Earth developed oceans or continents, the sun was once a volatile T-Tauri star surrounded by a swirling disk filled with the building blocks of future planets. The early solar system was not peaceful. It was chaotic, and the young sun was partly responsible. One of the defining traits of T-Tauri stars is rapid rotation. Young stars spin much faster than older mature stars like the present-day sun. The reason goes all the way back to the collapse of the original molecular cloud. As the cloud contracted inward, rotation sped up dramatically through conservation of angular momentum, much like a spinning ice skater pulling their arms inward. Even after the star forms, much of that rapid rotation remains, and rapid rotation changes everything. Inside stars, rotating plasma generates magnetic fields through processes collectively known as stellar dynamos. Faster rotation strengthens these dynamos enormously. Combined with vigorous convection inside the star, the result is extreme magnetic activity. Young stars become magnetic monsters. Their surfaces erupt constantly with powerful flares and plasma ejections. Magnetic loops twist and reconnect violently. Radiation storms flood surrounding space. Some flares from T-Tauri stars release thousands of times more energy than typical solar flares produced by the modern sun. Imagine the strongest solar storm humans have observed, then increase it dramatically. That was the kind of environment surrounding the infant Earth. And unlike today's relatively stable sun, T-Tauri stars can vary unpredictably in brightness. Material from the surrounding disk may fall onto the star unevenly, causing sudden bursts of energy release. Magnetic interactions between the star and disk create additional fluctuations. Some young stars brighten unexpectedly. Others dim for periods as dust clouds pass in front of them. Some pulse irregularly for years. They behave less like stable stars and more like cosmic weather systems. This variability confused astronomers initially. Early observers noticed certain stars changing brightness erratically, without understanding why. Only later did scientists realize these were extremely young stellar objects still evolving rapidly. In many ways, T-Tauri stars are stars still trying to settle down, and the surrounding protoplanetary disk plays a major role in that instability. The disk is not simply passive debris orbiting quietly around the star. It remains an active dynamic structure filled with turbulence, collisions, magnetic interactions, and streams of infalling gas. Material from the inner disk often spirals inward along magnetic field lines before crashing onto the stellar surface. These accretion flows can become spectacular. Gas accelerated by magnetic forces slams into the star at enormous speeds, heating localized regions to very high temperatures. Hotspots form across the stellar surface. Radiation bursts outward. X-rays flood nearby space. Young stars essentially feed from their disks magnetically. The process looks incredibly complicated in modern simulations. Streams of plasma arc between the disk and star like gigantic glowing bridges. Magnetic fields stretch outward into surrounding space. Stellar winds interact with infalling material continuously. The entire system remains unstable and turbulent for millions of years. Meanwhile, planets are trying to form inside the disk during all this chaos. That part still feels slightly unbelievable. Imagine attempting to build stable worlds inside an environment flooded with radiation storms, stellar winds, magnetic eruptions, and violent accretion bursts. Yet somehow, planetary systems emerge repeatedly. The early solar system almost certainly experienced this environment. Ancient meteorites preserve evidence of intense heating events and energetic radiation exposure during the sun's T-Tauri phase. Tiny mineral grains inside certain meteorites appear to have formed under flash heating conditions likely connected to violent solar activity. The young sun was far more aggressive than today, and its behavior strongly influenced the developing solar system. One especially important effect involved the solar wind. T-Tauri stars produce powerful stellar winds capable of clearing away remaining gas from the surrounding disk over time. This process effectively limits how long giant planets can continue gathering hydrogen and helium from the nebula. Timing matters enormously. If a giant planet forms early enough, it may accumulate a massive atmosphere like Jupiter or Saturn. If gas disperses too quickly, only smaller rocky planets remain possible. The young star partly determines the architecture of its planetary system through these violent winds, and those winds become extremely strong during the T-Tauri phase. Modern observations reveal some young stars producing outflows extending for light years. Jets and winds carve cavities through surrounding nebulae while dispersing leftover gas. Eventually, the stellar nursery itself begins fading away as more and more material gets blown outward into interstellar space. The star slowly clears its surroundings, and while all this happens externally, major changes continue inside the star too. Young sun-like stars contract gradually during the T-Tauri phase. Although hydrogen fusion has begun, the star has not yet fully stabilized onto the main sequence. Gravity still compresses the star slowly over time. As contraction continues, the star becomes smaller, hotter, and denser. The modern sun is significantly more compact than it was during its infancy. That means the young sun actually shone somewhat differently than today. Surprisingly, many models suggest the infant sun may have been slightly dimmer overall, despite its greater activity. This creates an interesting scientific puzzle known as the faint young sun paradox. Evidence suggests liquid water existed on early Earth billions of years ago. But if the young sun emitted less total energy back then, Earth should theoretically have been frozen. So why wasn't it? Scientists suspect greenhouse gases in Earth's early atmosphere may have trapped additional heat. Methane, carbon dioxide, and other gases likely played major roles in maintaining habitable conditions despite the dimmer sun. The paradox remains an active area of research even today. Young stars continue creating mysteries long after astronomers begin understanding them. Another fascinating aspect of T-Tauri stars is their interaction with planetary migration. Inside protoplanetary disks, forming planets do not necessarily remain where they originated. Gravitational interactions with the disk can cause planets to drift inward or outward over time. The giant planets in many exoplanet systems appear to have migrated dramatically during their early histories, and the evolving young star influences these processes through radiation, winds, and disk structure. The infant years of solar systems are astonishingly dynamic. Planets collide, orbits shift, gas disperses, asteroids bombard young worlds continuously. Meanwhile, the central star erupts with violent magnetic storms. The early solar system probably resembled organised chaos at best, and not every young star behaves exactly the same way. Mass matters enormously again. Low-mass stars may remain magnetically active for very long periods. Massive stars evolve too quickly for extended T-Tauri phases, and instead move rapidly toward more advanced stages of stellar evolution. Sun-like stars occupy an interesting middle ground. They spend millions of years as unstable, active young stars before gradually calming down. That gradual calming process is important for planetary habitability. Extremely violent stellar activity can strip atmospheres away from nearby planets, especially smaller rocky worlds lacking strong magnetic fields. Mars may have suffered partly from this effect. Early in solar system history, solar winds likely contributed to stripping much of Mars's atmosphere after its magnetic field weakened. Earth survived partly because of its magnetic field. Our planet's molten iron core generates a protective magnetosphere deflecting many charged particles from the solar wind. Without that shield, Earth's atmosphere might have evolved very differently under the young sun's assault. Life on Earth owes more to magnetism than many people realize, and young stars make that protection especially important. Astronomers studying exoplanets now pay close attention to stellar youth and activity because they strongly affect planetary evolution. Some red dwarf stars, for example, remain highly active for enormous spans of time, producing intense flares capable of bombarding nearby planets repeatedly. A planet orbiting close to such a star may experience constant radiation storms for billions of years. Habitability becomes complicated quickly. Still, T-Tauri stars eventually settle down. Over millions of years, stellar winds remove surrounding gas and dust. Rotation gradually slows. Magnetic activity decreases. The star contracts fully onto the main sequence. Stability emerges slowly. The Sun followed this path too. Its furious childhood eventually faded into the relatively steady mature star humans know today. Solar flares still occur, of course. Coronal mass ejections still erupt occasionally. The solar wind still streams outward through the solar system. But compared to its T-Tauri years, the modern Sun is remarkably calm. Middle age changes stars too. One especially beautiful aspect of studying T-Tauri stars is realizing that astronomers are effectively looking backward in time at the Sun's own childhood. The Orion Nebula, for example, contains many young stars currently passing through stages the Sun once experienced. Some possess protoplanetary disks, likely forming planets right now. Others launch jets through surrounding gas, or erupt with variable brightness. Somewhere inside those disks, future Earth-like worlds may eventually emerge, perhaps with oceans, perhaps with atmospheres, perhaps with beings who someday study astronomy themselves, all while orbiting stars currently behaving like unstable stellar teenagers. Modern telescopes continue revealing extraordinary details about these systems. The James Webb Space Telescope has captured stunning images of protoplanetary disks surrounding young stars, showing rings, spirals, gaps, and evolving structures with remarkable clarity. Some disks already display evidence of forming planets, despite the youth of the system. Planetary construction begins surprisingly early, and through all of this, the star itself continues maturing slowly. Its core settles into stable hydrogen fusion. Its outer layers reorganize. Its magnetic field gradually weakens. Its violent childhood slowly fades. Eventually, after millions of years of instability, the star becomes something much calmer, a mature sun, reliable, stable, predictable enough that planets can orbit peacefully for billions of years. But before that calm arrives, every star passes through this strange turbulent adolescence, a phase of storms, radiations, magnetic violence and cosmic chaos. While the young star struggles through its unstable childhood, something equally remarkable begins unfolding around it. The leftover material surrounding the star does not simply disappear, it starts building worlds. At first, this process seems almost absurdly unlikely. The protoplanetary disk surrounding an infant star is mostly gas mixed with tiny dust grains, smaller than smoke particles. The disk stretches across enormous distances yet remains incredibly thin compared to its width. Turbulence churns through it continuously. Radiation from the young star floods nearby space. Magnetic fields twist through the gas. Nothing about the environment feels calm or organized, and yet somehow, from this chaotic rotating disk, planets emerge, rocky worlds, gas giants, moons, asteroids, comets. Entire future solar systems begin assembling themselves grain by grain inside the turbulent debris orbiting around newborn stars. The process starts very small. Microscopic dust grains drifting through the disk collide constantly. Most early collisions are gentle enough that the particles stick together through electrostatic forces. Tiny clumps form, then slightly larger clumps. Over time, grains become pebbles. That may not sound impressive initially, but remember, every mountain, ocean, forest, and city on Earth ultimately began through processes like this inside the young solar system. Everything starts as dust. The first steps are actually among the strangest parts of planetary formation, because tiny particles behave differently from large objects. Dust grains drifting through gas experience drag forces similar to air resistance on Earth. Turbulence stirs them continuously. Static electricity helps them cling together. Some collisions help growth, others shatter particles apart again. Astronomers still actively study these early stages because the transition from microscopic grains to larger solid bodies remains surprisingly complicated. Nature somehow solves engineering problems before humans even fully understand them. Eventually, some clumps become large enough that gravity itself begins helping the process. Once objects grow beyond certain sizes, their own gravitational pull attracts additional material more effectively. Growth accelerates. Pebbles become rocks. Rocks become kilometre-sized planetesimals. And now the disk starts becoming crowded with countless young worlds in progress orbiting around the infant star. The early solar system likely contained millions upon millions of these bodies. Most no longer exist. Many collided and merged into planets. Others shattered apart. Some were ejected entirely from the solar system through gravitational interactions with giant planets. The young solar system was less like a tidy orbital diagram and more like a giant demolition derby happening at orbital speeds. And collisions mattered enormously. Every major planet grew through repeated impacts with smaller bodies. Earth itself formed gradually as countless planetesimals merged together over millions of years. Some collisions were relatively gentle, others catastrophic. One impact probably changed Earth forever. According to the giant impact hypothesis, a Mars-sized object called Theia collided with the young Earth roughly 4.5 billion years ago. The collision was unimaginably violent. Huge quantities of molten rock and vaporized material blasted into orbit around Earth. Eventually, that debris formed the Moon, which means the Moon may literally exist because planetary formation was so chaotic. Without cosmic violence, Earth's night sky might look very different, and the collisions did not stop there. Throughout the early solar system, impacts occurred constantly. Asteroids slammed into forming planets. Giant bodies migrated through the disk, disturbing smaller objects gravitationally. Young planetary systems are dangerous places. Modern telescopes now allow astronomers to observe some of these processes unfolding around other stars. The James Webb Space Telescope and radio observatories like Atacama Large Millimeter Array have captured extraordinary images of protoplanetary disks surrounding infant stars, and the disks are beautiful. Some display bright rings separated by dark gaps. Others contain spirals, arcs, or asymmetrical structures stretching across enormous distances. Certain gaps may indicate young planets already forming inside the disk and clearing pathways through surrounding material. Astronomers are essentially watching solar systems under construction. That realization still feels remarkable. Human beings evolved around one mature planetary system, and for most of history had no direct evidence of how such systems actually form. Now telescopes routinely capture images of worlds emerging around distant young stars. Some disks appear so organized they almost resemble giant vinyl records orbiting through space. Others look chaotic and turbulent. Again, environment matters enormously. Closest to the young star, temperatures become extremely high. Only rocky and metallic materials can survive there because lighter compounds vaporize under the intense heat. Farther outward, cooler conditions allow ices to remain stable. This temperature difference shapes the architecture of planetary systems. In our solar system, the inner rocky planets formed relatively close to the Sun, where temperatures were too high for volatile compounds like water ice to survive easily. Farther outward, giant planets formed in colder regions rich in ices and gas. Astronomers call the boundary separating these regions the frost line or snow line. Beyond this line, giant planets can grow much more rapidly because icy materials provide abundant additional mass. Jupiter likely formed beyond the solar system's frost line, gathering enormous quantities of gas before the young sun's stellar wind dispersed the remaining nebula. Timing was critical. If Jupiter had formed too slowly, much of the gas might have vanished before it could become a giant planet, and giant planets strongly influence everything else around them. As Jupiter grew, its gravity reshaped the solar system dramatically. It scattered nearby planetesimals, altered orbital paths, prevented certain regions from forming planets entirely. The asteroid belt between Mars and Jupiter may exist partly because Jupiter's gravity disrupted planetary formation there. Large planets become architects of solar systems, and planetary migration complicates things even further. For a long time, astronomers assumed planets generally remained where they formed. Then scientists began discovering exoplanets in bizarre orbits impossible to explain under older models. Some giant planets orbit extremely close to their stars, much closer than Mercury orbits the Sun. These hot Jupiters could not have formed easily in such hot environments. The solution was migration. Young planets can drift inward or outward through interactions with the surrounding disk. Giant planets especially may move enormous distances during early system evolution. This means solar systems are not static during formation. Planets wander. Some spiral inward toward destruction. Others get flung outward. Some collide. The early years of planetary systems resemble organized chaos barely held together by gravity, and all the while the young star itself remains unstable too. T-Tauri stars continue blasting radiation and stellar winds into the surrounding disk. Strong ultraviolet light alters chemistry within the gas. Magnetic fields interact with the disk continuously. Jets erupt from the poles. Planet formation unfolds under difficult conditions. One especially fascinating part of this process involves water. Water exists widely throughout molecular clouds and protoplanetary disks, often frozen as ice in colder outer regions. Many scientists believe Earth's water may have arrived partly through impacts from icy asteroids or comets originating farther from the Sun. In a sense, Earth's oceans may have travelled inward across the solar system during its chaotic youth. That possibility changes the way you think about ordinary rain slightly. Some of the water molecules inside Earth's oceans may predate the Sun itself, inherited from the original molecular cloud that formed the solar system. Older than Earth, older than the planets. Ancient molecules surviving stellar birth and planetary formation. The chemistry inside protoplanetary disks becomes surprisingly rich too. Astronomers detect organic compounds, carbon-bearing molecules, water vapour, and many other complex chemicals within these environments. The ingredients for future biology begin gathering long before life exists, which means the path toward habitable worlds starts astonishingly early, even before planets fully form, and not every planetary system develops like ours. That is one of the most important discoveries of modern astronomy. For much of human history, people naturally assumed the solar system represented a fairly standard arrangement. Then astronomers began discovering exoplanets, thousands of them, and many systems turned out to be wildly different. Some possessed giant planets orbiting extremely close to their stars. Others contain tightly packed systems of rocky worlds. Some feature planets in highly elongated orbits. Some stars host multiple giant planets interacting gravitationally. Certain systems may contain free-floating rogue planets, ejected entirely from their birth systems. Nature experiments constantly. The solar system is only one outcome among countless possibilities, and those outcomes begin taking shape during the disk phase around infant stars. The amount of material in the disk matters. The timing of gas dispersal matters. Stellar mass matters. Giant planet formation matters. Nearby stars inside crowded stellar nurseries matter. Even passing stars may occasionally disturb developing systems. Planetary formation becomes a giant chain reaction of interconnected processes. One especially dramatic phase in our own solar system may have occurred several 100 million years after formation. According to the Nice model, giant planets migrated significantly during the early solar system, destabilizing enormous populations of smaller bodies. This migration may have triggered the Late Heavy Bombardment, a period when impacts across the inner solar system increased dramatically. The Moon still preserves evidence of many ancient impacts from this era. The early solar system remained unstable for a very long time, and yet somehow, from all that violence, stable planets eventually emerged. Earth settled into a relatively circular orbit. The Moon stabilized Earth's axial tilt. Oceans formed, life appeared, which feels slightly miraculous considering how chaotic the beginning was. Modern observations of young planetary systems reveal that our solar system's story was probably not unusual in its turbulence. Astronomers regularly observe disks with enormous gaps, asymmetries, collisions, and evolving structures. Some systems may currently be undergoing giant impacts similar to those that once shaped Earth. Others show evidence of active planet migration. We are effectively watching other solar systems experience their own violent childhoods, and through all of this, the central star slowly matures too. Over time, stellar winds disperse the remaining gas from the disk. Once the gas disappears, giant planet formation largely stops. Leftover dust gradually becomes incorporated into planets, moons, asteroids, or comets. The chaotic disk slowly clears. A mature planetary system begins emerging from the debris, not perfectly ordered, but more stable. And somewhere inside many of those systems, rocky planets may eventually cool enough for oceans, atmospheres, and perhaps life. all because dust grains once collided gently inside rotating disks around unstable infant stars. That chain of events still feels almost impossible when traced backward properly. Every tree, every animal, every human being, every city, every memory, all ultimately connected to tiny grains of dust drifting around a young violent sun billions of years ago. About 4.6 billion years ago, long before Earth existed, before oceans formed, before dinosaurs walked or continents drifted into their present shapes, the sun itself was hidden inside a cold, dark cloud, drifting through a quiet region of the Milky Way. No human being saw it happen, of course. The solar system formed unimaginably long before eyes capable of observing stars even evolved on Earth. But modern astronomy has become surprisingly good at reconstructing ancient events from the clues left behind. Meteorites preserve chemical fingerprints from the solar system's infancy. Telescopes reveal young stars currently passing through similar stages. Computer simulations model collapsing clouds and protoplanetary disks. Piece by piece, scientists have assembled a picture of what the sun's birth probably looked like, and it was nothing like the calm yellow star hanging in the sky today. The young sun was turbulent, violent, magnetically unstable, surrounded by chaos, and everything familiar about modern Earth began inside that instability. The story likely started inside a giant molecular cloud somewhere within one of the Milky Way's spiral arms. This cloud contained hydrogen, helium, dust grains, and heavier elements produced by older stars that had lived and died before the sun formed. That detail matters enormously. The sun is not a first-generation star. It belongs to a later generation born from material already enriched by previous stellar deaths. Ancient supernovas seeded the cloud with carbon, oxygen, silicon, iron, and countless other elements. The raw materials for planets already existed before the sun itself formed. In a sense, the solar system inherited cosmic leftovers, and something disturbed the cloud. Astronomers still debate exactly what triggered the collapse. One leading idea involves a nearby supernova explosion. Evidence preserved inside certain meteorites suggests short-lived radioactive isotopes existed during the solar system's infancy. These isotopes likely formed inside a nearby massive star shortly before the sun was born. That means the death of one star may have helped create another. A shockwave from the explosion could have compressed part of the molecular cloud, pushing it past the threshold where gravity took over. Then collapse began. The cloud fragment that eventually became the solar system probably measured far larger than the modern planetary system itself. As gravity pulled the material inward, rotation increased. Most of the mass gathered toward the center, while the remaining material flattened into a spinning disk. At the center of the disk, the protosun began forming. Around it, the solar nebula stretched outward across enormous distances. Everything familiar today existed only as gas, dust, and future possibilities. The early sun itself was still dark at first, at least in visible light. Dense dust surrounding the forming protostar blocked much of the radiation escaping outward. But inside the collapsing core, temperatures and pressure continued rising steadily. Meanwhile, the surrounding disk churned continuously. Tiny grains collided and stuck together. Larger clumps formed. Shockwaves rippled through the disk. Magnetic fields twisted through the gas. The infant solar system was dynamic from the very beginning, and it was probably crowded too. Astronomers strongly suspect the sun formed inside a stellar cluster, alongside many sibling stars. Most stars do not form in complete isolation. Giant molecular clouds fragment into groups of collapsing cores, producing clusters of newborn stars within the same general region. That means the sun likely had neighbours. Some of them may have been massive stars flooding nearby space with ultraviolet radiation. Others may have possessed their own growing planetary systems. Over millions of years, gravitational interaction slowly scattered these sibling stars throughout the galaxy. Today, they are probably impossible to identify with certainty. Somewhere in the Milky Way, though, stars born beside the Sun still exist, ancient siblings wandering the galaxy unnoticed, and during the Sun's earliest years, those neighbouring stars may have influenced the solar system significantly. Massive nearby stars could have shaped the outer edges of the solar nebula through radiation and stellar winds. Supernova explosions may have compressed certain regions while dispersing others. The Sun's birth environment was likely far more crowded and energetic than the relatively quiet neighbourhoods surrounding the solar system today. Then came the protostar phase. The infant Sun continued gathering mass from the surrounding disk while gravity compressed its core inward. Temperatures climbed steadily. Jets erupted from the poles. Magnetic activity intensified, and eventually the Sun became a T-Tauri star. This stage may have been one of the most violent periods in solar system history. The young Sun rotated faster than it does today. Rapid rotation strengthened its magnetic field enormously. Giant flares erupted frequently. Powerful stellar winds blasted outward into surrounding space. The Sun was effectively throwing cosmic tantrums. Ancient meteorites preserve evidence of this activity. Some contain tiny melted inclusions called chondrules, small spherical droplets likely formed by flash heating events in the early solar system. Scientists suspect energetic solar outbursts may have contributed to creating these structures. The young Sun left fingerprints inside the rocks that eventually became planets. Meanwhile, inside the surrounding protoplanetary disk, planets were beginning to form. Closest to the Sun, temperatures remained extremely high. Only rocky and metallic materials could survive there. This region eventually produced Mercury, Venus, Earth, and Mars. Farther outward, cooler conditions allowed water ice and volatile compounds to remain stable. Giant planets formed there more easily because abundant ice increased the amount of solid material available. Jupiter likely formed relatively early and grew rapidly. That timing mattered enormously. Once Jupiter became sufficiently massive, its gravity started reshaping the entire solar system. It scattered nearby planetesimals, influenced orbital paths, and possibly migrated inward and outward during the solar system's youth. Some models suggest Jupiter may have moved significantly before settling into its current orbit. Imagine the largest planet in the solar system wandering through the early planetary disk like a giant gravitational bulldozer. The young solar system was not a calm, orderly arrangement of neat circular orbits. It was chaos barely held together by gravity. Collisions happened constantly. Young planets slammed into one another repeatedly. Asteroids and planetesimals bombarded growing worlds continuously. Entire protoplanets may have formed and later vanished through collisions or ejections. Earth itself experienced one of the most important collisions in solar system history. According to the giant impact hypothesis, a Mars-sized body called Theia collided with the young Earth roughly 4.5 billion years ago. The impact released unimaginable energy. Huge quantities of molten rock blasted into orbit around Earth. That debris eventually became the Moon. The modern Earth-Moon system may literally exist because planetary formation was so violent, and the Moon changed Earth profoundly afterward. Its gravitational influence stabilized Earth's axial tilt, affecting climate stability over geological timescales. Tides shaped coastal ecosystems. The length of Earth's day evolved gradually through tidal interactions. One ancient collision altered billions of years of planetary history, and all of this happened while the Sun itself was still young and unstable. The early Sun's radiation and stellar wind strongly influenced planetary atmospheres too. Mercury lost much of its volatile material under intense solar heat. Mars may have gradually lost much of its atmosphere after its magnetic field weakened. Earth survived partly because of its molten iron core generating a protective magnetic field. Without Earth's magnetosphere, the young Sun's activity might have stripped the atmosphere away far more aggressively. Life on Earth owes something to magnetism and to timing. Another fascinating clue about the Sun's birth comes from the outer solar system. Far beyond Neptune lies the Kuiper Belt, a vast region filled with icy bodies left over from planetary formation. Beyond even that may stretch the Oort cloud, an enormous spherical reservoir of comets, extending perhaps nearly halfway to the nearest stars. These distant regions preserve ancient debris from the solar system's infancy. Many comets contain relatively unaltered material dating back to the solar nebula itself. In a sense, they are frozen time capsules preserving chemistry from before the planets fully formed. Some water molecules inside modern comets may predate the Sun. That idea feels almost impossible at first. Matter inside your body may once have drifted through interstellar clouds before the solar system existed. The universe recycles everything eventually. And over time, the young Sun gradually calmed. Its rotation slowed. Magnetic activity weakened. The solar wind dispersed most of the remaining gas from the protoplanetary disk. Planetary formation slowed as leftover debris either became incorporated into planets or got scattered away. The violent childhood of the solar system slowly faded into relative stability, but traces of those early years remain everywhere. The heavily cratered surfaces of the Moon and Mercury preserve evidence of ancient bombardment. Meteorites preserve isotopic clues about stellar explosions predating the Sun. The arrangement of planets reflects migration and gravitational interactions from billions of years ago. Even Earth's existence depends on those chaotic beginnings unfolding exactly as they did. Modern astronomy gives us remarkable ways to visualize what the Sun's birth may have resembled. Observatories like the James Webb Space Telescope now capture detailed images of young stellar systems in various stages of evolution. Some resemble what the solar system probably looked like during the protostar phase. Others show T-Tauri stars surrounded by turbulent disks. Some reveal giant gaps where planets may already be forming. Astronomers are effectively looking backward in time at analogues of the Sun's childhood. The famous Orion Nebula likely contains many systems currently resembling the early solar system. Young stars there blaze inside fading nebulae, while disks of gas and dust spin around them. Inside some of those disks, future Earth-like planets may eventually emerge, perhaps with oceans, perhaps with atmospheres, perhaps with life. The universe may have repeated the solar system's story countless times already. That possibility changes the night sky slightly once it settles into your thoughts. The stars overhead stop feeling ancient and unreachable. Instead, they become part of an ongoing cycle still happening throughout the galaxy. Some stars are old, some are newly born, and somewhere tonight inside dark stellar nurseries, new suns are still awakening exactly as ours once did, surrounded by spinning disks, blasted by magnetic storms, building planets grain by grain inside turbulent clouds. The Sun itself began as one more unstable infant star hidden inside darkness. Nothing about its early years suggested that one small rocky planet would eventually develop forests, oceans, animals, civilizations, music, mathematics, or people lying awake at night wondering how stars are born. And yet here we are, still orbiting the same star that once fought its way out of a collapsing nebula billions of years ago. One of the biggest misconceptions people have about stars is imagining them forming alone in quiet isolation. It makes intuitive sense from a human perspective. We look at the Sun sitting by itself in our sky and naturally assume stars generally emerge as solitary objects scattered independently throughout space. But the universe usually does not work that way. Stars are social at birth. Most form together in groups, clusters, or crowded stellar families inside giant molecular clouds. Entire generations of stars may emerge from the same collapsing region almost simultaneously, sharing common origins before slowly drifting apart across the galaxy over millions or billions of years. The Sun itself almost certainly had siblings. Long ago, somewhere inside a dark stellar nursery, our star formed alongside many others from the same collapsing cloud. Over time, those siblings scattered throughout the Milky Way until their shared birthplace became nearly impossible to trace. Somewhere tonight, stars born beside the Sun may still be orbiting the galaxy quietly. Ancient relatives separated long before Earth even existed. That realization changes the way you think about the night sky. Stars stop feeling isolated and begin resembling members of enormous extended families spread across the galaxy. And stellar nurseries are where those families begin. The reason stars form together comes directly from how molecular clouds collapse. Giant molecular clouds are not smooth uniform structures. They are turbulent, filamentary, chaotic regions filled with dense knots and clumps. As gravity compresses these clouds, the material fragments repeatedly. Instead of producing one giant star, the cloud breaks apart into many collapsing cores. Each core may become a separate star. Sometimes only a few stars form in a small region. Other times thousands emerge together inside massive stellar nurseries. The famous Orion Nebula contains a young cluster called the Trapezium cluster, where many hot young stars formed relatively close together. The surrounding nebula glows because these stars flood nearby gas with ultraviolet radiation, and Orion is only one example among countless others throughout the Milky Way. Some star clusters become enormous, globular. Clusters, for example, may contain hundreds of thousands of stars packed into relatively compact regions. These clusters are ancient, among the oldest surviving structures in galaxies. Open clusters are generally younger and looser. The famous Pleiades, visible to the naked eye as a small, sparkling group of blue stars, formed together from the same molecular cloud relatively recently in astronomical terms. The stars of the Pleiades are essentially siblings still travelling together through space, and over time clusters slowly disperse. Gravitational interactions between stars gradually alter their motions. Nearby molecular clouds tug on them. Galactic tides stretch and scatter them. Eventually many clusters dissolve entirely, their stars spreading across the galaxy. That is probably what happened to the Sun's birth cluster. Astronomers estimate the Sun may originally have formed alongside hundreds, or perhaps thousands of sibling stars. Today those siblings are lost among the Milky Way's hundreds of billions of stars. Finding them is extraordinarily difficult because after billions of years, stars drift far from their birthplaces. Still, scientists continue searching. Some studies attempt to identify possible solar siblings based on chemical composition and orbital motion. Stars born from the same cloud often share similar chemical fingerprints because they formed from the same raw material. It is a bit like cosmic genealogy. Except the family members are stars, and the family reunion spans the entire galaxy. One especially fascinating thing about stellar clusters is how much the environment influences star formation itself. Young stars born close together do not evolve independently. They affect one another constantly. Massive stars dominate the environment dramatically. A hot O-type star may emit enormous quantities of ultraviolet radiation capable of ionizing surrounding gas and stripping material from nearby protoplanetary disks. Stellar winds carve cavities through the nebula. Supernova explosions later send shock waves racing through the cluster. The larger stars become cosmic bullies. Meanwhile, smaller stars forming nearby must survive inside those conditions. This can strongly influence planetary formation. In dense clusters, radiation from massive stars may erode protoplanetary disks before planets fully form. Some young planetary systems may lose gas too quickly to build giant planets. Others survive relatively intact. Again, outcomes depend heavily on environment. Our own solar system may preserve clues about its crowded birthplace. Certain isotopes found in ancient meteorites suggest the young sun formed near at least one massive star that later exploded as a supernova. That nearby explosion may have injected radioactive elements into the early solar system. In a sense, the Sun grew up in a dangerous neighbourhood, and clusters themselves can become remarkably dynamic places. In very dense stellar environments, stars occasionally pass relatively close to one another. These encounters can disrupt planetary systems, alter comet reservoirs, or even eject planets entirely. Imagine entire worlds being thrown into interstellar space because two stars passed near each other millions of years earlier. Astronomy escalates consequences aggressively. Some free-floating rogue planets discovered in recent years may have originated this way. Formed around stars, then later ejected through gravitational interactions during the chaotic early evolution of stellar clusters. Not every planet gets to keep its home star. Binary star systems also become extremely important here, because many stars form in pairs or larger multiple star systems rather than alone. In fact, binary systems may be extremely common throughout the galaxy. Some estimates suggest roughly half of Sun-like stars belong to binary or multiple systems. For massive stars, the fraction may be even higher. That means solitary stars like the Sun might actually be somewhat unusual. The night sky is full of stars orbiting other stars, and these systems can become wonderfully complicated. Some binaries orbit closely, completing revolutions in only days. Others remain widely separated. Certain systems contain 3 or more stars locked in intricate gravitational dances. Planet formation inside such environments becomes far more complicated too. Imagine trying to maintain stable planetary orbits while 2 suns move through the sky instead of 1. Yet planets around binary stars absolutely exist. Astronomers have discovered many examples already. Nature seems comfortable building planetary systems under conditions humans once considered impossible. The birth of binary stars likely begins during fragmentation inside collapsing molecular clouds. Instead of one dense core forming, rotation and turbulence sometimes produce multiple nearby cores orbiting one another gravitationally. 2 stars begin growing together. In some systems, the stars exchange material later in life. In others, they remain relatively separate. Certain binaries eventually create spectacular phenomena like X-ray binaries, novae, or even gravitational wave events when compact remnants collide. A star's siblings can shape its fate long after birth. Clusters also help astronomers study stellar evolution because stars inside a cluster generally form around the same time. That means differences between them primarily reflect mass rather than age. The Pleiades, for example, contains many young blue stars still relatively early in their lifetimes. Older clusters contain more evolved populations because massive stars have already died. By comparing different clusters, astronomers essentially reconstruct stellar aging. Clusters become cosmic laboratories. And they are beautiful too. There is something quietly moving about seeing hundreds or thousands of stars sharing a common origin. Human beings naturally think in terms of individual objects, but the universe often creates structures collectively. Stars emerge together, live together for a time, then drift apart gradually. The process feels strangely familiar somehow. Even the Milky Way itself likely grew partly through mergers, involving ancient stellar clusters and dwarf galaxies. Modern observations reveal stellar streams stretching across the galaxy, remnants of clusters and small galaxies torn apart gravitationally over time. Nothing in astronomy remains fixed forever. One particularly fascinating class of cluster is the globular cluster. These ancient dense clusters orbit the outskirts of galaxies and contain some of the oldest stars in existence. The Omega Centauri, for example, contains millions of stars packed tightly together. If Earth somehow orbited a star inside the dense central regions of such a cluster, the night sky would look astonishingly crowded. Multiple bright stars might appear as luminous as the moon. Constellations would barely exist because stars would fill huge portions of the sky. It would feel less like living beneath isolated suns and more like existing inside a glowing swarm. Fortunately for our sleep schedules, the solar system formed in a less crowded region. Still, even our relatively modest birth cluster likely shaped the solar system significantly. Close stellar encounters early in the Sun's history may have influenced the outer solar system. Some theories suggest passing stars perturbed objects in the distant Kuiper belt or helped shape the Oort cloud. The solar system did not evolve in complete isolation, and modern stellar nurseries reveal these crowded conditions clearly. The Tarantula Nebula contains enormous star-forming regions filled with dense clusters of young stars. Massive stellar winds and radiation carve intricate cavities through surrounding gas while new stars continue forming nearby. It is essentially cosmic urban development, crowded, chaotic, noisy, and full of ongoing construction. The Eagle Nebula and Orion Nebula reveal similar processes closer to home. Young stars illuminate surrounding gas, while dense knots inside the nebula continue collapsing into future generations. Some stars inside these nurseries may already possess forming planets. Others may lose their disks quickly under intense radiation from nearby giants. Again, environment changes everything. One especially important consequence of clustered star formation involves chemical enrichment. Massive stars born inside clusters evolve quickly and explode as supernovas. Those explosions scatter heavy elements across nearby regions, enriching future generations of stars and planets. The universe recycles itself through clusters repeatedly. One generation dies, another forms from the debris, and over billions of years, galaxies gradually become richer in heavy elements capable of building rocky planets and complex chemistry. Without earlier generations of stars, Earth could never have existed. Clusters are part of that larger cycle, and despite the violence and chaos involved, there is something comforting about the idea that stars rarely begin alone. Even the Sun once belonged to a stellar family, before billions of years of galactic motion scattered everyone apart. Perhaps somewhere, one of the Sun's ancient siblings still drifts through the Milky Way surrounded by planets of its own. Maybe icy worlds, maybe rocky planets, maybe nothing at all. The galaxy is large enough for every possibility, and while older clusters slowly dissolve across the Milky Way, new ones continue forming right now inside dark molecular clouds. Dense regions collapse, young stars ignite, radiation floods nearby gas, clusters emerge from fading nebulae. Another stellar family begins its long journey through the galaxy together, before time gradually pulls it apart again. Tonight we followed a story that began in darkness. Not empty darkness, but the kind filled with hidden things. Cold molecular clouds drifting quietly through the galaxy, dust grains floating for millions of years, gravity pulling patiently on matter so gently that nothing seems to happen at first. And then, slowly, stars begin waking up. A cloud collapses, a protostar forms, heat rises inside the core, fusion ignites, radiation floods outward, planets gather themselves together from leftover dust, orbiting around unstable young suns. Entire solar systems emerge from material that once drifted invisibly between the stars. The remarkable part is that this process is still happening constantly. The Milky Way has not finished building stars. Far from it. Even now, somewhere beyond the night sky above your home, enormous stellar nurseries remain hidden inside dark clouds. Young stars are turning on for the first time. Protoplanetary disks are spinning around them. New planets are colliding and forming in environments so violent and chaotic that early Earth itself would probably have looked familiar there. Some of those stars may eventually host rocky worlds, some may possess oceans, some may never form planets at all, and some may already be beginning stories we cannot yet imagine. That idea changes the night sky slightly once you really let it settle in your thoughts. The stars overhead stop feeling fixed and eternal. Instead, they become part of an ongoing cycle. Birth, growth, change, collapse, renewal. One generation creating the ingredients for the next. The universe recycles itself endlessly. The iron in your blood once existed inside ancient stars. The oxygen you breathe was forged in stellar cores long before Earth formed. Even the calcium in your bones was created through processes connected to stellar birth and death. You're not separate from this story. You are one small continuation of it. That realization can feel strangely comforting late at night. Human life often feels very small compared to cosmic scales, and in many ways it is. Stars live for billions or even trillions of years. Galaxies evolve across spans of time almost impossible for the human brain to visualize properly. And yet the atoms making up your body came directly from those ancient cosmic processes. The universe did not simply produce stars. Eventually, through stars, it produced chemistry complicated enough for oceans, forests, animals, music, memory, language, and quiet moments like this one. All beginning from clouds drifting silently through darkness. There is also something deeply humbling about how patient the universe is. A star may spend millions of years preparing for ignition. Planetary systems require tens or hundreds of millions more to stabilize. Life on Earth took billions of years to evolve from simple organisms into beings capable of asking where stars come from in the first place. Nothing rushed. Gravity did not rush. Fusion did not rush. Galaxies did not rush. The cosmos seems entirely comfortable allowing extraordinary things to emerge slowly. Human beings struggle with that sometimes. We want quick answers, quick progress, quick certainty. But nearly everything important in the universe forms gradually. Stars, planets, life, even galaxies themselves, all built patiently over immense spans of time. And despite the violence we explored tonight, despite the flares, collisions, radiation storms, supernovas, and chaotic stellar nurseries, the larger process somehow still produces remarkable stability in the end. The sun eventually calmed, Earth cooled, oceans formed, the sky became blue, life spread across the planet, which means every ordinary sunrise carries a hidden history behind it. The warm sunlight falling across streets, forests, windows, and oceans today traces back to a star that once fought its way out of a collapsing cloud billions of years ago. The sun was once invisible inside darkness too. That feels worth remembering occasionally, especially because stars can seem so permanent from our perspective. They rise reliably every night. Constellations appear fixed. The sky feels timeless. But every star has a beginning. Every star in the sky once existed as drifting dust inside a cold molecular cloud somewhere in the galaxy. Even the oldest stars visible tonight were once newborns hidden inside stellar nurseries. And somewhere tonight, future stars are still forming. That means the universe remains unfinished. There are stars that do not exist yet. Planets that do not exist yet. Perhaps entire future civilizations orbiting suns that are still only collapsing clouds tonight. The cosmos is still creating new things in the darkness. Maybe that is part of why people have always looked upward with such fascination. The night sky feels ancient, but it also feels alive. Not alive in a biological sense, of course. Galaxies are not conscious. Nebulae are not thinking quietly to themselves about astrophysics. Though honestly, if they were, they would probably understand it better than we do. Still, the universe is active, dynamic, ongoing. It changes continuously whether humans notice or not. Stars ignite, stars die, new clouds collapse, the cycle continues. And somehow, inside that enormous process, one small planet developed creatures capable of lying awake late at night listening to stories about stellar birth, while the real stars continue shining overhead. That is a very strange thing for the universe to produce. Before we finish tonight, I want you to picture something simple. Imagine standing beneath a perfectly dark sky far away from cities. The Milky Way stretches overhead like a pale river of light crossing the darkness. Thousands of stars shimmer quietly above you. Some are ancient. Some are relatively young. Some may already be dead, their light still travelling toward Earth. and hidden between them are enormous cold clouds invisible to your eyes. Inside those clouds, gravity is still working patiently. Dust grains continue colliding, protostars continue warming, fusion continues igniting for the first time. The galaxy is still building stars while you rest here tonight. That process will continue long after this evening passes, long after human civilizations change, long after continents shift again. The universe will keep creating stars in darkness and silence, because that is simply what gravity and time eventually do together. And somewhere very far from Earth, another young sun is probably opening its eyes for the very first time right now. So as you settle in a little deeper tonight, let your thoughts drift gently through those quiet stellar nurseries one last time. Through the cold clouds, the spinning disks, the newborn stars, and the future planets still gathering themselves together, grain by grain inside the darkness. Because every star in the sky began there, as dust, as silence, and as the slow, patient work of gravity unfolding across the universe.